Yes, sir. Yes, sir.
Right. So I'm going to screen. So please let me know if you can see my screen.
Yes, sir. This
Yes,
is
sir.
All right, and now I will be taking the attendance. So please try to respond to your ID. You can see the attendance sheet, right?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
All right then. Please try to respond to your serial. Serial 1,
Present, sir. Present, sir.
2, 3,
Present, sir.
4,
Present.
5, 6,
Yes, sir. Present.
Yes, sir. Yes, sir. Present. Yes, sir. Present.
7, 8,
Present, sir. Sir.
9,
Present, sir.
10, 11,
Yes, sir.
Yes, sir.
12,
Yes, sir.
13.
Present, sir.
স্যার স্ক্রিন দেখা যাচ্ছে না
Screen
স্যার
দেখা যাচ্ছে না, sir.
Can you see my screen?
Yes,
Yes, sir. Yes, yes, sir.
No, sir.
Okay, good.
Yes, sir.
Yes, sir. Step. Sir. 10. Sir. 10.
14, are you present or not? Okay, 15,
Yes, sir. Yes, sir.
16,
Yes, sir.
17,
Present, sir.
স্ক্রিন দেখা যাচ্ছে না স্যার
Screen দেখা যাচ্ছে না, sir.
18,
Present, sir. Present, sir. 80.
19,
Yes, sir. Yes, sir.
20, 21,
প্রেজেন্ট স্যার
Present, sir.
22,
Yes, sir. Yes, sir.
23,
Present, sir. Present, sir.
24,
প্রেজেন্ট স্যার
Present, sir.
25,
Present, sir.
Present, sir.
26,
Yes, sir.
27,
Present, sir. Present, sir.
28, 29,
Present, sir. Present, sir.
30,
Present, sir. Present, sir.
31,
ইয়েস স্যার
Yes, sir.
32,
Present, sir.
Present, sir.
33,
Present, sir. Present, sir.
34, 30,
পরে স্ক্রিন দেখা যাচ্ছিল না বলছো।
প্রেজেন্ট স্যার প্রেজেন্ট স্যার
35,
Present, sir. Present, sir.
35 present, 36,
34 প্রেজেন্ট স্যার
37,
34. Present, sir.
38,
Present, sir. Present, sir.
39, 40,
প্রেজেন্ট স্যার
Present, sir.
Sir,
41,
present.
Sir.
41,
14 present. 14 present.
41. Okay. So now from serial 1 to 10, anyone present?
Sir,
From
14.
1 to 10.
Yes, sir. Yes, sir. Subscribe. Start 34 present করেছিল।
Can you please wait for your turn? I mean, I'll be visiting your ID. So it is always good to have a bit of patience. All right. From serial 1 to 10, anyone present? I mean, those who couldn't give your attendance. 2, all right. Anyone else from 1 to 10?
স্যার নাম্বার
From 11 to 20?
Sir, 14 present. 14 present.
Anyone else? 11 to 20? Okay, from 21 to 30? From 21 to 30, anyone? Okay, no. From just 1 minute. 31 to 40.
34
Sir,
present, sir.
37.
Okay, 37, then 31 to 41.
34, sir.
Anyone else?
34, sir.
34. Okay, anyone else? Okay, so I think we are done with our attendance. So let us move to the class. So in today's class, we are going to start a new experiment that you can see. And this will be the experiment 5 for this semester, which is the introduction to particle swarm optimization for dynamic system simulation. So this experiment will fall under the broad class of optimization. All right. And optimization itself is a vast topic. So I wanted to introduce you to the fundamental of optimization. All right. And if you look into the course description of ours, let me show you that. Yeah. If you look into this PDF that you get over here, you will be able to see that we have the optimization within our course content. I mean, if we look over here, so we have the optimization, right? So that's why I thought that maybe this semester I'm going to show some optimization skills, and it will help you later on as well, because in engineering we use optimization quite a lot. All right. So that's the case. I mean, if I give the outline of the class that we are going to take today, first I am going to give some brief introduction on optimization itself, and after that it will be a discussion on the particle swarm optimization. I mean, we are going to have the basic idea about that. After that, we are going to take some problem from the RLC system. All right. We already know that our course will be revolving around the dynamic system or the RLC system that we are interested in. And we are going to solve a problem regarding damping, how we can optimize the parameters from one RLC circuit in order to get the optimized value from our damping. All right. And we are also going to see how damping can affect our system. So this is how we are going to proceed throughout the class. Yes? Anyone want? Sorry?
স্যার অ্যাটেন্ডেন্সের সময় হচ্ছে আমার স্ক্রিন দেখা যাচ্ছিল না, সো হচ্ছে আমি বের হয়ে গিয়েছিলাম, পরে হচ্ছে আর এন্ট্রি পাওয়া যাচ্ছিল না।
All right. In that case, I am not going to take the attendance any further. All right. So
স্যার আমি ইনকল মেসেজ
I am now trying to start the class. So it will be really nice of you if you can please cooperate a bit. All right. I mean, you can say that I have already started the class. So just follow with the class, and later on we can see what we can do. Can you have the patience or not?
Yes, sir.
Whatever. So yeah. So let us start the thing. So first, as you can see that, well, let me show you from here. It will be much better. I can also mark the things a bit as well. So can you tell me, I mean, do you have any idea regarding the optimization? I mean, can you tell me in a few words, I mean, where we use optimization, or have we used optimization so far in our academics or something like that? Can you give me some hints? So I think we already used optimization, right? I mean, can you recall calculus, the basic of calculus? Can you remember that? Because that is going to help us with the very basics of optimization. Optimization is not something that we are starting just today. We had our experience with optimization. I mean, if I ask you that, let me write something. Okay.
What's the problem?
So if I ask you that, let's show from here. So if I give you one function, suppose this is one function, right? Which is x minus 3 whole square. So this is one function, and this function will look like this, something like this. This is one parabola and it will start from 3. So this is the function that we have. So can you tell me at which point are we going to get the minimal value? I mean, by the way, can you hear me?
Yes, sir.
Okay.
X equals to 3.
I can increase the sound. Okay. Yeah, I mean, definitely the root is available to us at 0.3. All right, x equals 3. So my question is, using calculus, how can we determine that? Can you tell me? I mean, how can we find the root? First, we have to take the first derivative, right? If I take the first derivative, that is going to give us the gradient or the slope. And what will be the first derivative of this function? That should be something like this, right? And after that, our rule of thumb is the maxima or the minima of our function will be available to us when I put this thing equals 0. So whenever the first derivative of our function is equals to 0, at that point, we can expect to get our maxima or minima. All right. I mean, it's not something like that we are going to get the minima only. We can also get the maxima as well. Suppose this function, if I draw something like this, if I draw a function like this, in that case, at what point will I get the maxima for the rate function that I tried to draw? This is plus y and this is minus y. So definitely at point x equals 3, I am also going to get the maxima for the rate function. And for the blue function, at point x equals 3, I am going to get the minima. All right. So that is why we say that whenever the first derivative of our function is equals 0, and if we solve that equation, we are going to get the point at which we are going to get either the minima or the maxima, depending on our function. So now, this is the very first case of optimization that we did using calculus, and this is known as the analytical optimization or analytical solution, whatever we call. So we are familiar with this. So now if I ask you that if there is any computational method for us, I mean, we do not want to do any calculus, we don't want to do any first derivative or something like that. So in that case, how can we proceed? So our option for that is we have to take the computational method into account and we have to exploit that. And what are the computational methods? There are a few computational methods that will depend on the problem actually. I mean, depending on the complexity of our problem, we can choose either the genetic algorithm or the particle swarm optimization algorithm, something like that. All right. So in this class, we are going to see how we can use the particle swarm optimization in order to take the optimization or in order to determine the minimized value. All right. So yeah, let's go back to the topic one more time. So let's see what are the basics of optimization. So as you can see that in this paragraph, it is saying that optimization is a core concept in fields as mathematics, engineering, and economics, aimed at finding the best possible solution. So this is the first thing that I want to mark. Using optimization, we are going to take the best possible solution within a set actually. All right, so we will be given one data space and we have to determine the best possible values from that data space for our solution. All right, and what are the key components of optimization? So this is very important. So first we need one objective function. So this is the function that we are going to optimize. All right. So if I show you this equation, we can say that this equation is the objective function. So I need some function. I need some mathematical terminologies and I am going to use my optimization algorithm on that. So for that reason, I need one objective function. So, if you just have a bit of patience and if you can bear with me, I am going to show this thing multiple times in this class. All right. And if you have any question, you can definitely ask that anytime. I mean, regarding the topic that we are discussing today. All right. So after that, the decision variables. All right. So can you tell me what is the decision variable from this equation? I mean, if this is the objective function, in that case, what can be the decision variable for this function?
So differentiating the function.
Well, actually, no. The answer is the variable, right? The variable is x. So this is the decision variable. So I have to decide what should be the value of this variable using optimization. So that is why this is the decision variable that we call. So first we have this optimization function, which we also call as objective function. And after that, we have this decision variable. And finally, there is one more thing, which is the constraint, right? So in this case, we do not have any constraint over here. In this case that we do not have any constraint. But what does the constraint usually mean? So suppose since we are going to deal with RLC circuit, let me give you the example with those. So suppose the value of R is within 1 ohm to 1 kilo ohm, something like this. So in this case, this is the constraint. I mean, this boundary that you can see, this is the constraint. So whenever I optimize the values, I have to respect this constraint. All right. So whenever I am making the optimization, I have to make sure that the value that I find, the solution that I get, that should be within this bound. All right. So this is the constraint. But for this case, the example that I have shown you, this was for the analytical method. And for that method, we do not have any constraint. We just used some direct calculus to get our value. But now we are not going to use the calculus. Rather than we are going to use some computational method. We are going to use some computational method in order to determine the optimization solution. All right. And usually we give constraint whenever the bound is fixed. If we do not fix the constraint, the problem will be unbounded. In that case, the iteration will take any value within the known horizon of numbers. And that is going to make our calculation complex. So it is always wise for us if we give some bound or if we give some constraint, because if I ask you regarding the values of resistor or inductor or capacitor, the values are always bound, right? I mean, it's unusual for us to use some really big value of resistors, or maybe we cannot even find the resistor in market as well. So it is always good for us to use some practical values, and for that case, usually in real life problems, we give some bound or we set some constraints. So that is the constraint. So these three things are the most basic things if we want to do some optimization: the objective function, the decision variable, and finally the constraint. So I think so far the things are clear. Or do you have any question from here? Well, all right. The objective function is the mathematical expression that defines the goal of the optimization, either seeking its minimum or maximum value. So there is a common misconception that whenever we are trying to do some optimization, people think that we have to minimize the value. But optimization doesn't mean to minimize the value. It can also mean to maximize the value as well. As I have tried to show you using this example over here of this, parabola. So for the blue parabola that we can see, the minimum value will be available to me at point x equals 3, right? But for the red parabola at x equals 3, at that point, the maximum value will be available to me. So in the second case, we are actually trying to maximize the value from the optimization. All right. So that's the case. And after that, the decision variables are the parameters that can be manipulated to achieve the desired outcome. For instance, in designing a filter, variables like resistance, inductance, and capacitance are the decision variables that influence the system's performance. We already know that the process typically involves adjusting decision variables to either maximize or minimize the function. So that's the case. I mean, we have to adjust the decision variables in such a way so that it can either maximize or minimize the function, and that will be given in our problem. All right. Okay, and what are the applications? The application or the goal can be to minimize the cost. I mean, whenever we are doing something, we have to optimize the cost, right? I mean, if you start your FYDP, maybe in your FYDPC, you have to do some hardware, right? And it is always wise for us if we try to make some budget planning ahead, because that will help us to optimize or minimize the cost. We do not want to do any redundant expenditure, right? So that's the thing actually. Similarly, if we have some system, if we are designing some system, we have to make sure that the system can replicate or imitate the actual scenario. All right. I mean, we have to always try to make the real system and the modeling of that system as close as possible. So we have to minimize the error, right? So this is where the application of the optimization can be implemented. In order to reduce the error, we can also use the optimization, right? Similarly, energy consumption, right? And finally, to maximize performance, efficiency, or profit. So these are the ideas that we can use for our optimization basic. All right. So now let's move ahead. So let's know a bit more regarding the constraint. So constraints in optimization are limitation or boundaries that the decision variable must adhere to. So as I have mentioned earlier, so if I am given a constraint within a boundary, the optimization algorithm or whatever we use, that is going to respect that boundary. That is not going to, leap out of that boundary. So for the capacitor, suppose I am giving a boundary of 1 microfarad to, let's say, 100 microfarad, something like that. Those are the practical values that we can even buy from the market as well. So, within this bound, the optimization algorithm that we have, that is going to respect this bound. That is not going to leap or cross this bound. All right. So this is the constraint. For example, there may be upper limit on the values of resistance, inductance, or capacitance, or a requirement that the sum of the components stay below a certain threshold. So yeah, that is another point, that maybe we have multiple components and we have to make sure that the summation of those components is less than one particular value, something like that. So that can be another constraint. And respecting the constraint, our goal is to find the best solution within the feasible space. Okay. And yeah, now let's learn about the types of the optimization that we can use. So as you can see here, optimization problems can be broadly categorized into various types, including unconstrained and constrained optimization. So if I ask you regarding this problem that I have shown you, definitely this is one analytical solution, but in this analytical solution, this is also one optimization, right? We are trying to get the value where the least amount of function value is present for x, right? And over here, as you can see, that we do not have any constraint for x. The x can take any value. So this problem over here is one unconstrained value. But over here for the RLC example that I have given, this is one constraint example because we have to respect the boundary of the values of RL and C. Okay. So in unconstrained optimization, decision variables can take any value, while in constrained optimization, the variables must satisfy certain limitations or restrictions. Optimization can also be linear or non-linear. So this is another point. The optimization that we are going to do, that can be either linear or non-linear, and it will depend on the objective function. All right. So the constraint and the objective function, that can be linear or non-linear, and based on that, the optimization method will also change. Right. And finally, the optimization method can also involve discrete variable. Okay, so this is important because from the first example, that was one continuous problem. All right. That was one continuous problem because that value of x can be anything within the real value of x. That was one continuous problem. But if I give one set like this, suppose this is value of r and the value can only be 1, 2 and 3. So this is one discrete set because if I use the optimization over here, the only option that I have is either 1, 2 or 3. I mean, I have just 3 options. But for this case, the one that you can see over here, since I have mentioned a boundary from 1 ohm to 1 kilo ohm, this is one continuous problem because the value of resistance for this case can be like 1.5, 1.7, something like that. And the problem that we are going to solve today using MATLAB will be one continuous problem as well. All right, we are going to get some fractional value. And yeah, now let's look at the methods that we can use. So different methods are used to solve optimization problems. Analytical method involve mathematical techniques such as calculus. So this is the example that I wanted to show you. Using calculus, how you can determine the optimization, how you can get the value where the function is minimal. Whereas computational methods like gradient descent, genetic algorithm, and particle swarm optimization are used for more complex problems. So, you are going to see, I mean, if we have some complex problem, we can use some advanced algorithms. All right. It actually depends on the problem. I mean, if our problem can be solved within, basic optimization techniques, we are not going to use the advanced ones. Okay. It always depends on the problem itself. These methods rely on algorithms to approximate solutions, especially in cases involving nonlinearities or large solution space. So what does it mean? Large solution space. So this is, suppose you can see that we have a range or a boundary over here, right? We have a range for R, we have a range for L, we have a range for C. So this entire set that we have of R, L, and C, this is the solution space. Okay, solution space will consist the boundary for all the decision variables. So we have 3 decision variable over here, which is R, L, and C, and the boundary or the values of those 3 variables will create the entire solution space. All right. The process of optimization aims to find the best solution, either maximizing or minimizing the objective function while ensuring convergence toward the optimal solution over iterations. So yeah, I tried to read this thing line by line so that I can give you some, overview on the entire thing. I mean, if you followed with me, I believe you had some good idea on these things. Do you have any question from this portion? Do you have any question? Well, computational method is one trial and error method. All right. So, this is one analytical method, right? I mean, just let me erase a few things. So the thing that you can see over here, the equation that I have circled with the red color. So this is one objective function. The function of x, you can call this as one objective function. But how am I going to determine the solution? For this case, I have taken the calculus method, and using that calculus method, I am going to get the value as 3. So this is one analytical method because we are directly using the concept of mathematics. We are not doing any trial or error or something like that. I mean, you can ask me what is trial and error. So this is how it goes. Suppose for iteration 1, I am taking the value of x as 1. In that case, what should be the value of f prime x? Can you tell me? That should be something like this, -4, right? Let's say if I increase the value of I from 1 to 2, in that case, what should be the value of f prime x? That should be something like this, right? 2 minus 3, it should be -2. So can you differentiate the way how I approach the solution? For the calculus solution that we did I do any trial and error? I mean, did I check the thing step by step?
Any computational method ক্ষেত্রে যদি আমার কোনো কন্টিনিউয়াস ভ্যালু থাকে সেটা কি দিতে পারবে?
ডেফিনেটলি পারবে। ইন দ্যাট কেস আমি তোমাকে যেটা দেখালাম সেটা হচ্ছে জাস্ট সহজে বোঝানোর জন্য। যদি আমার স্টেপ সাইজ এরকম হয় 0.1, তাহলে কি হবে? প্রথমে 1, তারপরে কি 2 আসবে? না, তখন কিন্তু আসবে 1.1, রাইট? জিনিসটা কি বুঝতে পারছো? জিনিসটা হচ্ছে যে আমি স্টেপ কিভাবে নিচ্ছি। আমি এখানে ইজিলি তোমাকে দেখানোর জন্য জাস্ট দুইটা এক্সাম্পল দিয়ে দেখালাম। আমি আই, যেটা সেই আই এর ভ্যালু 1 বা 2 নিয়ে যদি আমি চেক করি যে এফ প্রাইম এক্স এর ভ্যালু কত, দেখো একবার -4 আর একবার -2 এসছে। তো আমি কিন্তু একটা জিনিস বলতে পারি যে এখনো কিন্তু আমি আমার বেস্ট সলিউশনে যাই নাই, কারণ এখনো ভ্যালুটা কি হচ্ছে, কমতেছে। তো এরপরে আমি যখন এফ প্রাইম এক্স এ আই ইকুয়ালস 3 তে যখন 3 বসাবো, তখন কি পাবো? 0 পাবো। তো এই জায়গায় আমার ভ্যালু এখন পর্যন্ত সবচেয়ে কম, রাইট? তারপরে যদি আমি 3 থেকে ভ্যালুটা বড় করি, তখন কি হবে বলতো? যদি আমি এখানে 4 নেই, তখন কি পাবো? 4 - 3, তখন ভ্যালু কত আসবে? 2। আবার কি ভ্যালুটা বেড়ে যাচ্ছে না? তো একটা জিনিস খেয়াল করছো যে একটা রেঞ্জ পর্যন্ত এসে ভ্যালু আবার বাড়া শুরু করছে। তো আমার এখানে প্ল্যান ছিল আমি সবচেয়ে কম বা ছোট ভ্যালুটা নিব এক্স এর যেই ভ্যালুটার জন্য ওয়াই এর ফাংশন আমি সবচেয়ে ছোট পাবো, সেই ভ্যালুটা আমি এখান থেকে বের করব। তো এটা আমি এখানে কিভাবে বের করতেছি? আমি কিন্তু ট্রায়াল এন্ড এরর করে বের করতেছি, রাইট? আমি কিন্তু প্রত্যেকটা স্টেপে চেক করতেছি যে এই ভ্যালু কি আগের ভ্যালুর থেকে ছোট কিনা। যদি ছোট হয় আমি পরেরটায় যাচ্ছি, পরেরটা যে চেক করতেছি যে এই ভ্যালু কি আগেরটার থেকে ছোট কিনা। যদি ছোট হয় আমি সামনে যাব, যদি ছোট না হয় বুঝবো যে এটাই আমার সবচেয়ে ছোট সলিউশন, রাইট? যেমন আমি যখন এক্স এর ভ্যালু 2 এর জন্য -2 পেলাম, আমি কি করলাম? পরের স্টেপে গেলাম, এক্স এর ভ্যালু 1 ইনক্রিজ করে আমি 3 করে পরের স্টেপে গেলাম, আমি 0 পেলাম। 0 পাওয়ার পরে কি করলাম? এটার ভ্যালু আরো 1 বাড়ালাম, বাড়িয়ে আমি 4 এ গেলাম। বাট 4 এ যাওয়ার পর আমি কি দেখলাম? আমি দেখলাম যে ভ্যালু 0 থেকে আর কম হচ্ছে না, রাইট? ফাংশনের ভ্যালু কিন্তু আর 0 থেকে কম হচ্ছে না। আমি বলতে পারি যে এই 0ই হচ্ছে আমার অপটিমাইজড ভ্যালু বা মিনিমাল ভ্যালু। So this is how I am determining that value, and since we are using the trial and error method, this is one computational method. So আমার এখন কোশ্চেন হচ্ছে, আমি যদি এই হাতে ট্রায়াল এন্ড এরর মেথড করতে যাই, আমার কি অনেক সময় লাগবে কিনা বলো? আমি যদি এখন এই হাতে হাতে জিনিসটা বের করতে যাই, এটা কি আমার অনেক সময় লাগবে কিনা, কি মনে হয়?
এই জন্য কি স্যার ফর লুপের ক্ষেত্রে ইউজ করব যে আমার কোনো
এক্স্যাক্টলি,
কিছু হয়ে
এবং
গেলে for loop
সেজন্য এটাকে আমরা কম্পিউটেশনাল মেথড বলি, বুঝছো? যেহেতু এগুলো বাস্তবে হাতে হাতে বের করাটা প্র্যাকটিক্যাল না, আমরা কি করি? আমরা কম্পিউটেশনাল টেকনিক গুলো ইউজ করি শুধুমাত্র যখন আমার হাই কম্পিউটেশনাল এফিসিয়েন্সি থাকবে। যেমন আমাদের কম্পিউটার দিয়ে আমরা প্রায় সেকেন্ডের মধ্যে অ্যাটলিস্ট 10 মিলিয়ন সিমুলেশন করতে পারি, তাই? অনেক হিউজ সিমুলেশন আমরা করতে পারি, অনেকগুলো ভ্যালু বের করতে পারি। আমরা যখন ম্যাটল্যাব ইউজ করি, আমরা কিন্তু আলটিমেটলি কি বের করি? প্রত্যেকটা পয়েন্টের এগেইনস্টে ম্যাট্রিক্সের যে ভ্যালু সেটাই তো বের করি, রাইট? বাট আমরা কি অনেকগুলো ভ্যালু কি একসাথে বের করতে পারি না? মানে একবার রান দিলে কি সবগুলো ভ্যালু একসাথে আসে না? অনেক অনেক ভ্যালু আসে না? লেটস সে 1000 বা লাখ, এই রেঞ্জের ভ্যালু আমরা সাথে সাথে পাই না? এই সাথে সাথে যে পাচ্ছি, এটা যদি আমি হাতে করতে যাই, এটা ডেফিনেটলি অনেক সময় লাগবে। তো এই জন্যই এই ট্রায়াল এন্ড এরর মেথড যেগুলো, সেগুলোকে আমরা কম্পিউটেশনাল মেথড বলি, কারণ এগুলো আমরা মূলত কম্পিউটেশনাল পাওয়ার থাকলে শুধুমাত্র তখনই করি। জিনিসটাকে বুঝতে পারছো? ঠিক আছে, তো এই জন্যই আমরা যে আজকে পিএসও দেখবো, এটা হচ্ছে একটা কম্পিউটেশনাল মেথড, কারণ এখানে অনেকগুলো ট্রায়াল এন্ড এরর হবে। এখানে আমাদের যে ভ্যালু, সেই ভ্যালুগুলোকে আমরা প্রিভিয়াস ভ্যালুর সাথে কম্পেয়ার করব, করতে করতে আমরা একটা লোয়েস্ট পয়েন্টে যাব। যাওয়ার পরে আমরা আবার দেখবো যে এর থেকে কি কম ভ্যালু আমার পাওয়া পসিবল কিনা। যদি হয় সেটাকে আমরা রাখবো, যদি না হয় আমরা সামনে চলে যাব। জিনিসটা হচ্ছে এরকম। বাট আমরা এখানে যে অ্যানালিটিক্যাল মেথড ইউজ করলাম, সেখানে কি এরকম কোনো ট্রায়াল এন্ড এরর ছিল? না। আমরা কিন্তু সরাসরি আমাদের ম্যাথমেটিক্সের যে কনভেনশন, যেটা হচ্ছে যে ফার্স্ট ডেরিভেটিভের ভ্যালু যদি আমি 0 সমান রাখি, তাহলে আমি এক্স এর যে ভ্যালু পাবো সে হয় মিনিমা অথবা ম্যাক্সিমা, এই দুটোর একটা আমাকে দিবে। আমাদের কনভেনশন সহজ এবং শেষ। আমাদের কিন্তু ফার্দার আর কিছু করতে হয় না, রাইট? আমরা সরাসরি ভ্যালুটা যে 3 এটা বের করে ফেলছি। বাট কম্পিউটেশনাল মেথডে কি আমরা এরকম কোনো কনভেনশন ইউজ করছি? কি মনে হয় বলতো? আমরা কিন্তু করি না।
ট্রায়াল এন্ড এরর।
আমরা কিন্তু করি না, আমরা প্রত্যেকটা পয়েন্ট ধরে ধরে দেখছি যে কোন পয়েন্টের জন্য ভ্যালু কম, যে পয়েন্টে ভ্যালু কম সেটা কি আমরা রাখছি, রাইট? তো এটাই হচ্ছে কম্পিটিশনাল মেথড, যেগুলো আমরা কম্পিটিশনাল পাওয়ার থাকলে করতে পারি এবং যেখানে ট্রায়াল অ্যান্ড এররটা হচ্ছে বেস। ঠিক আছে, এইখানে সলিড ম্যাথমেটিক্সের থেকেও বেশি প্রয়োজন হচ্ছে ট্রায়াল অ্যান্ড এরর। আমার জাস্ট চেক করে দেখতে হবে কোন মেথডটা কেমন। এটা হচ্ছে ইটারেটিভ মেথডও এই জন্য আমরা বলি, কারণ এখানে আমরা অনেকগুলো ইটারেশন নেই, রাইট? যেমন এখানে আমি 4টা ইটারেশন নিলাম, একটু পরে একটা কোড দেখাবো, সেখানে 50টা বা 100টা ইটারেশন নিয়ে আমরা করতে পারি। তো সলিউশনের আউটপুট ডিপেন্ড করবে ইটারেশনের উপরে। আমি যত বেশি ইটারেশন চালাবো আমি বলতে পারবো যে আমার সলিউশনটা হয়তো তত অ্যাকুরেট। ঠিক আছে, এবং সবচেয়ে ইম্পর্টেন্ট বিষয় হচ্ছে বেশিরভাগ ক্ষেত্রে আমাদের কম্পিউটেশনাল মেথডগুলো আমাদেরকে অ্যাপ্রক্সিমেট সলিউশন দেয়। ঠিক আছে, আমরা এক্সাক্ট অথবা অ্যাবসলিউট সলিউশন তখনই পাবো যখন আমরা এক্সাক্ট মেথড ইউজ করি। বাট আমরা যদি কোনো কম্পিউটেশনাল মেথড ইউজ করি, মেজরিটি কেসে সে আমাকে একটা অ্যাপ্রক্সিমেট ভ্যালু দিবে। তাহলে তুমি আস্ক করতে পারো যে তাহলে কেন আমরা করব কম্পিউটেশনাল মেথডটা ইউজ করব অ্যানালিটিক্যাল মেথড ইউজ না করে? তো এটার আরেকটা অ্যান্সার হচ্ছে, আমি তোমাকে খুবই ইজি একটা ইকুয়েশন দিয়ে জিনিসটাকে বোঝানোর ট্রাই করছি, বাট আমার যদি খুব কমপ্লেক্স একটা ফাংশন থাকে, খুবই কমপ্লেক্স একটা ফাংশন যেখানে ভ্যারিয়েবল হচ্ছে অ্যাটলিস্ট 1000-এর উপরে, রাইট? আমরা যখন স্টেট স্পেস করি আমরা কিন্তু দেখছি যে আমাদের কিন্তু ভ্যারিয়েবল অনেকগুলো হতে পারে। যদি এমন কোনো কমপ্লেক্স ইকুয়েশন থাকে যেখানে 1000টার উপরেই ভ্যারিয়েবল থাকবে, তখন তুমি আমাকে বলো যে অ্যানালিটিক্যাল মেথড ইউজ করাটা কি এত সহজ হবে? অবশ্যই হবে না। তো সেই জন্য যেটা আগে থেকে বলে আসলাম যে কমপ্লেক্স যদি কোনো প্রবলেম থাকে সেখানে আমরা কম্পিউটেশনাল মেথড ইউজ করি, তাহলে এই ট্রায়াল এন্ড এররটা ইন দ্যাট কেস অনেক সাফিসিয়েন্ট। ঠিক আছে, ট্রায়াল এন্ড এররটা, এবং আমরা যেহেতু কম্পিউটেশনাল মেথড ইউজ করি দেখা যায় যে আমাদের সময় অনেক কম লাগে। ঠিক আছে, তো এটা হচ্ছে তোমার কোশ্চেনের অ্যান্সার, যেটা সময় নিয়ে দিলাম। আসো এরপরে দেখি আমরা। So here are the key steps in an optimization problem. So I'll be just going briefly on those, all right, because majority of the things are already discussed quite well. Define the objective function. So this is the first thing that we need to do. I mean, we need to define one objective function, because without the objective function, we will have no base to do the optimization, right? I mean, we need some sort of equation to optimize, and that equation will be our objective function. All right. Then identify decision variables. So that will also depend on the problem. For our case that we are going to do today, that will have 3 decision variables, the R, L, and C, these 3 things. After that, specify constraints. I mean, if we have some bound, if we have some boundary or range of values that we need to consider, that is known as the constraints, and we have to respect that as well. Choose an optimization method. So yeah, so far we know that we have so many different types of optimization methods. We have analytical method, we have computational method, we have linear, non-linear, we have constrained or unconstrained. So we have to choose our optimization method, and depending on our problem we have to choose that. We are not going to choose that randomly. All right. Solve and analyze the solution, and finally we have to solve the optimization problem for the given objective function, and we have to check for the optimum solution. All right. So this is the overview of the optimization. I mean, to be very frank, optimization is a huge topic. I mean, if you do one 6-month semester on optimization, I think that is going to be half sufficient or something like that. I'm just trying to give some very basic overview on those in like 30 minutes or something. All right. So now if you have a good idea on those, maybe we can move into the main topic of our class, which is the particle swarm optimization. So far we already have known what the optimization is, but in this particle swarm optimization method we are going to use some nature inspiration. We are going to take the inspiration from nature. I mean, this is not any rigorous mathematical problem, rather than this is one solution that is derived from the intuition or derived from the inspiration of nature. All right. So before starting this topic, let me show you something, or let me do something. Suppose, have you ever seen a flock of birds flying? Have you ever seen that? have you ever seen a swarm of bird flying in the sky?
Yes, sir.
So have you seen that they always try to follow a pattern? I mean, they do not fly randomly. Rather than they follow a pattern, right? Or if you look into the fish, I mean, the fish in the ocean, you will see that they create a vortex, and this is how they swim. So that is the inspiration of this particle swarm optimization method. All right. So you can ask that why are they revolving in one vortex in the ocean for the fishes actually? So the answer is they try to minimize the amount of energy that they lose while they swim. So that is the answer. They try to optimize their energy, and that is why they create that vortex. All right. So similarly, that is the case, I mean, where we are going to take our inspiration from. And for the particle swarm optimization, as the name itself says, there is a swarm, right? There is a swarm. I mean, suppose, let me give you another example in a different way. Suppose this is some food for a bird. All right. And we have like 3 birds over here. 1, 2, 3. I know they do not look like bird, but for our convenience, let us consider that these 3 are birds. So, you know, these 3 birds can do 2 things. Suppose they can explore the space by themselves as an individual. Suppose this bird is first moving in this direction, after that it is going in this direction, after that this something like that. Similarly, the bird that you can see, it is going in this direction. And finally we have the third bird, and suppose this bird is following in a different way to get the food or something like that. So now my question is, so how can we optimize this problem? I mean, I want these 3 birds to get the food at the same time. So how can I do that? You can see that if the 3 birds take 3 different paths, they can never get the food in the same time or in the same path, something like that. So how can I optimize this thing? Suppose I do not know the location of this food. Suppose this food is not visible to me. This food is not visible to me in my eyes. So I have to search the food like a blind or something like that. But I have 2 things in my hand. I have the current status of my position, and I know what the 2 other birds are at. I mean, what is the position of the 2 other birds? I also know that. So in that case, how can I do that? And there is one thing, I also know how much close I am to the food. These are the 3 things that I know. I know my position, I know the position of the other birds, and I know how close I am to the food. So how can I optimize the things? First, if I am doing good, if I am closer to the food, in that case, I can follow my trajectory, right? But if I am not closer to the food, in that case, what should I do? I will check which bird is closer to the food, right? Did you get my point? I mean, did you
Yes,
get my
sir.
point or not? So the thing is,
স্যার
I have, হ্যাঁ বলো।
স্যার ওই ক্ষেত্রে ক্লোজার যে বারটা ওর ট্র্যাজেক্টরি যে টাইমটা ওটা কম লাগার মতো।
হ্যাঁ সেটাই লাগবে যে পাখিটা কাছাকাছি থাকবে তার জন্য অবশ্যই সময় কম লাগবে, যার ট্রাজেক্টরি যতটা লিনিয়ার তার জন্য সময় তত কম লাগবে। বাট যেটা আমার কোয়েশ্চেন, ধরো এইখানে যে পাখির জন্য ফুড, এটা তুমি দেখতে পাচ্ছ না, এটা তোমার দেখার কোনো অপশন নাই। তোমার হাতে 3টে জিনিস আছে, সেটা হচ্ছে তোমার কারেন্ট পজিশন, অন্যান্য যে 2টা পাখি আছে তাদের কারেন্ট পজিশন, এবং তুমি এই ফুডের কত কাছাকাছি আছো সেইটা। এই 3টা জিনিস তুমি জানো, এবং অন্য 2টা পাখির কারেন্ট পজিশন জানার সাথে তুমি আরো একটা জিনিস জানো, সেটা হচ্ছে যে অন্য 2টা পাখির কত সময় লাগবে এই ফুডটা পেতে। ইন দ্যাট কেস জিনিসটা তুমি কিভাবে অ্যারেঞ্জ করতে পারো আমাকে বলো তো।
এটা ক্লোজেস্ট হচ্ছে ও পাথ থেকে চলে যাবে।
এক্স্যাক্টলি, ভেরি গুড। এটাই হচ্ছে আমার এখানের ওয়েটা। যেমন এই যে 3 নাম্বার পাখি যেটা, দেখো এটার ডিরেকশন কিন্তু পুরাই অন্যদিকে, রাইট? মানে যেদিকে ফুড তার কোনো দিকেই না, বাট একটা পয়েন্ট যাওয়ার পরে সে কিন্তু তার ট্রাজেক্টরিটাকে ফিক্স করা ট্রাই করতেছে, রাইট? তো এটা সে কিভাবে ফিক্স করতে পারবে? ধরো আমি যদি পাখির কথা বলি, তার কিন্তু লেটস চোখ আছে, সে দেখে সেই দিকে অ্যাডজাস্ট করতে পারে। বাট আমাদের যে ম্যাথমেটিক্যাল প্রবলেম, সেখানে এজন্যই বললাম যে অন্য দুইটা পাখি তার পজিশন জানতে পারবে, বা সে এখন কোথায় আছে সে এটা জানবে। ঠিক আছে, এটা যদি সে জানতে পারে তাহলে কি করতে পারে? সে যখন দেখবে যে এই রাস্তা অনুসারে আমার যেহেতু সে ফুডের কাছাকাছি যেতে যেতে পারতেছে, সে সেইভাবে তার ট্রাজেক্টরিটাকে অপটিমাইজ করা ট্রাই করবে বা সেট করার ট্রাই করবে। তো এই জন্য একটা পর্যায়ের পর সে আবার এই দিকে আসার ট্রাই করবে, রাইট? সিমিলারলি যে পাখিটা এই দিকে যাওয়া শুরু করলো, সে কি করবে? সে একইভাবে যখন দেখবে যে প্রথম পাখিটা ফুডের অনেক কাছাকাছি চলে যাচ্ছে, বা তার হয়তো বা ট্রাজেক্টরিটা ধীরে ধীরে ফুডের কাছে তাকে নিয়ে যাচ্ছে, সে কি করবে? সেও তার ট্রাজেক্টরিটাকে ধীরে ধীরে আবার সেই দিকে নিয়ে দিবে, তাই না? তো এইটা হচ্ছে আমাদের এই পিএসও অ্যালগোরিদমের ওয়ে। ঠিক আছে, একই সাথে আমার নিজের ট্রাজেক্টরির একটা হিসাব থাকবে, অন্য ভ্যারিয়েবল গুলোর যে ট্রাজেক্টরি সেগুলোর একটা হিসাব থাকবে, এবং আরেকটা জিনিস থাকবে যে আমি আমার গোলের কত কাছাকাছি। ঠিক আছে, যেমন আমি যে একটা জিনিস বললাম, এখানে আমার গোল কি কেউ বলতে পারবো আমাকে? এখানে গোল হচ্ছে আমি ফুডের কত কাছাকাছি, রাইট? আমি কি একটা জিনিস অলওয়েজ করার ট্রাই করতেছি, সেটা হচ্ছে আমি আমার কারেন্ট পজিশনের সাথে কি এই ফুডের ডিস্টেন্সটা কমানোর ট্রাই করতেছি না? এটাই কি আমি অপটিমাইজ করার ট্রাই করতেছি না? কি মনে হয় তোমার, বলো তো? ভেরি গুড, আমি কিন্তু এটাই করার ট্রাই করতেছি। এটাই হচ্ছে আমার গোল। এবং দেখো, বেস্ট সলিউশন যে পাচ্ছে, বাকিরা কি তাকে ফলো করার ট্রাই করতেছে না? জিনিসটা কিন্তু সেটাই। এখন তুমি আজ করতে পারো যে তাহলে এই তিনজনকে আনার উদ্দেশ্য কি, তাই না? এখানে তো একজনকে আমি রাখলেও পারতাম, একজনই ঘুরে ফিরে এক্সপ্লোর করে বের করতো। তিনজনকে রাখার কারণ হচ্ছে আমার প্রবাবিলিটি বাড়ানো। এর আগের ক্লাসে আমরা কিন্তু একটা স্ট্যাটিস্টিক মডেল দেখলাম, তাই না? আমাদের একটা ক্লাস ছিল মন্টি কার্লোর উপরে, যেখানে কিনা র্যান্ডমনেস ছিল। তো এইখানেও সিমিলার, যদি আমি এখানে
বাড়ালে আমার আয়ের মানে সমান তো।
হ্যাঁ, অনেকটা। এখানে পাই এর কোনো কথা আমি বলি নাই, বা পাই এখানে আসার কথা না, বাট জিনিসটা হচ্ছে র্যান্ডমনেস এর একটা ফ্যাক্টর এখানে থাকবে। যেমন আমি যদি এখানে অনেকগুলো স্যাম্পল নেই, বা আমার যদি এখানে পাখি অনেকগুলো থাকলো, ধরো আমার এখানে 3টে পাখির জায়গায় ধরো এখানে আমার 1000 পাখি থাকলো। ঠিক আছে, লেটস সে আমার 1000 পাখি এখানে আমি রাখলাম, তাহলে কি এইটা বেশি প্রবাবল না যে হয়তোবা যে কোনো একটা পাখি বাকিদের থেকে একটু কুইক, ইজিয়ার যে রাস্তা যেখানে সময় কম লাগে সেটা খুঁজে পাবে? এটা কি প্রবাবিলিটি কি আমাদের এটা বলে কিনা? কি মনে হয় তোমার, যদি আমার স্যাম্পল বড় হয়? যদি আমার স্যাম্পল বড় থাকে, আমি বলতে পারি না যে যে কোনো একটা পাখি হয়তো বা বাকিদের থেকে একটু কুইকলি ইজিয়ার পাথ যেটা, বা শর্টেস্ট যে ডিস্টেন্স সেটা খুঁজে পাবে? জিনিসটা কেমন না? এবং সে যদি সেই ইজিয়ার বা শর্টেস্ট পাথ খুঁজে পায়, তাহলে কি পুরো সোয়ার্ম তাকে ফলো করবে? আমাদের অ্যালগোরিদম কি সেটাই বলে না? যেমন যেটা তোমাদের এখানে দেখানো ট্রাই করলাম, যে একটা পাখি প্রথমে একটা রাস্তা খুঁজে পেলো, যেহেতু তার ডিস্টেন্সটা কম, এটা দেখে কি বাকি পাখিরাও কি তাদের ট্রাজেক্টরি চেঞ্জ করে তার মতো রাখার ট্রাই করছে? জিনিসটা কেমন না? তোমরা কি জিনিসটা বুঝছো? তো আমি আর একবার তোমাদের দেখাই, জাস্ট এইখানে ধরো, এবার ধরো 3টা পাখির জায়গায় আমি 5টা পাখি নিলাম সাপোজ। এই হচ্ছে আমাদের 5টা পাখি, এবং এই হচ্ছে আমাদের সেই গোল, অথবা ধরো এখানে সেই ফুড। ঠিক আছে, তো আমার কাজ হচ্ছে আমরা এক্সপ্লোর করব। কি এক্সপ্লোর করব? কোন রাস্তায় আমি এই ফুডটা পেতে পারি। ঠিক আছে, তো এখন প্রথমে এক্সপ্লোর করা শুরু করব কিভাবে? আমরা র্যান্ডমলি এক্সপ্লোর করা শুরু করব। ঠিক আছে, আমাদের পার্টিকেল সোয়ার্ম অপটিমাইজেশন মেথডের মধ্যে র্যান্ডমনেস থাকে। তোমাকে আমি এখনই দেখাই, লেটস সে আমি যদি দেখাই এই কোডের একটা পার্ট, এই যে দেখো এখানে কি একটা র্যান্ডম দেখতে পাচ্ছ তোমরা? তো এই র্যান্ডমনেস আমাদের পার্টিকেল সোয়ার্ম অপটিমাইজেশনের একটা পার্ট। আমরা যখন পার্টিকেল সোয়ার্ম অপটিমাইজেশন ইউজ করি, তখন সেখানে আমরা কিছুটা র্যান্ডমনেস ইনডিউস করি। তো সেই র্যান্ডমনেসটা আমি এখানে কিভাবে প্র্যাকটিক্যালি দেখাতে পারি? লেটস সে আমাদের এখানে 5টা পাখি, তো তো ধরো প্রথম পাখিটা এই দিকে যাওয়া শুরু করলো, পরেরটা এইদিকে যাওয়া শুরু করলো, পরেরটা এইদিকে যাওয়া শুরু করলো, একটা এইদিকে যাওয়া শুরু করলো, আর একটা এইদিকে যাওয়া শুরু করলো। সবাই কিন্তু তাদের র্যান্ডম একটা পজিশন থেকে যাত্রা শুরু করলো, রাইট? মানে ইনিশিয়াল পজিশন থেকে র্যান্ডম একটা ডিরেকশনে যাত্রা শুরু করলো। তো এইভাবে তারা যেতে থাকবে, মানে প্রত্যেকে একটা করে পজিশন আপডেট করতে থাকবে, মানে প্রত্যেকটা ইটারেশনে তারা র্যান্ডমলি তাদের পজিশন আপডেট করতে থাকবে। বাট তারা যদি অলওয়েজ এভাবে র্যান্ডম চলতে থাকে, আমি কি কোনো গ্যারান্টি দিতে পারবো যে তারা যে এখানে কনভার্জ করবে বা এই যে এখানে যেটা ফুড সেটা তারা পাবে? এটার কোনো গ্যারান্টি কি আমার দেওয়া পসিবল? দেওয়া পসিবল না। তো ইন দ্যাট কেস কি করবো, আমরা একটা কাজ করবো, সেটা হচ্ছে আমরা কিন্তু জানি যে প্রত্যেকটা পাখি এই মুহূর্তে কোন পজিশনে আছে, তাই না? বা প্রত্যেকটা পাখি এই মুহূর্তে কোন লোকেশনে আছে সেটা কিন্তু আমরা বলতে পারি। এবং সেই লোকেশন থেকে এই ফুডের ডিস্টেন্স কত সেটাও কিন্তু আমরা ক্যালকুলেট করে বের করতে পারি, রাইট? যদি আমাদের ভ্যালুগুলো দেওয়া থাকে কোঅর্ডিনেটের। এটা কি এগ্রি করো কিনা আমার সাথে? গুড। তো এখন আমি যদি দেখি, ধরো আমি একটা সেপারেট কালার নিই, আমি যদি দেখি যে একটা পাখি আমাদের ফুডের কাছাকাছি যাচ্ছে বা ধীরে ধীরে সে ডিস্টেন্স কমিয়ে নিয়ে আসতেছে বা এররটা কমিয়ে নিয়ে আসতেছে, দেখো এখানে কিন্তু একটা এররের কেস আছে, তাই না? আমি ডিস্টেন্স যত কমাবো, আমি বলতে পারি না যে আমি এররটাকে তত মিনিমাইজ করে নিয়ে আসতেছি, আমি তত সলিউশনটাকে অপটিমাইজ করতেছি। তো এখানে আমার অবজেক্টিভ ফাংশনটা কি কেউ বলতে পারবা? অবজেক্টিভ ফাংশন হচ্ছে ট্রাজেক্টরিটাকে খুঁজে পাওয়া, যে কোন রাস্তায় গেলে আমি এই ফুডটা পাবো, রাইট? তো যখন অন্যান্য পাখিগুলো দেখবে যে এই পার্টিকুলার পাখিটা ধীরে ধীরে এররটা কমায় নিয়ে আসতেছে, তখন বাকিরা কি করবে বলতো? বাকিরাও তাদের যে ট্রাজেক্টরি সেটাকে এই পাখির মতো অ্যাডজাস্ট করার ট্রাই করবে। ভেরি গুড। মানে তাদের কারেন্ট সিনারিও থেকে তারা ট্রাই করবে যেন এই পাখিটার মতো অ্যাডজাস্ট তারা করতে পারে। এরপরে তারা কি করবে, সবাই ধীরে ধীরে এই রাস্তায় আসা শুরু করবে। জিনিসটা এরকম। এখন আমার যদি স্যাম্পল অনেক বেশি থাকে, এখানে 5টার জায়গায় যদি ধরো 1,00,000 পাখি থাকলো, যদি এখানে 1,00,000 পাখি থাকে, জিনিসটা কি আর ইজিয়ার হবে না? যেহেতু আমাদের ইনিশিয়াল বেসটা আমরা র্যান্ডমনেস এর উপরে ভিত্তি করে করি, আমাদের এই যদি বলি সার্চ স্পেস, যেটাকে আমি বলবো যেটা সার্চ স্পেস, এই সার্চ স্পেসে কি আমি আরো এফিশিয়েন্টলি ট্রাভার্স করতে পারবো না বা সার্চ করতে পারবো না, আরো একটু এফিশিয়েন্টলি খুঁজতে পারবো না যদি আমার এজেন্ট বেশি থাকে? সহজ হিসাব ধরো, আমি জানি তোমরা হয়তো অনেকে ট্রেজার হান্ট খেলতা যখন ছোট ছিল, রাইট? ধরো একটা রুমের মধ্যে বা একটা অ্যাপার্টমেন্টের মধ্যে কেউ কিছু একটা রাখলো, তো একজন যদি জিনিসটা খোঁজে র্যান্ডমলি, তার থেকে যদি 10জন জিনিসটা খোঁজা শুরু করে, জিনিসটা পাওয়ার প্রবাবিলিটি একটু বাড়ে না? আমি বলবো না যে তারা পাবে, এটা গ্যারান্টেড না, বাট প্রবাবিলিটি কি বলে, যদি 10জন মিলে খোঁজা শুরু করে জিনিসটা পাওয়ার সম্ভাবনা একটু বাড়ে। জিনিসটা কি এরকম না? কি মনে হয়?
ওটা তো অবশ্যই বাড়বে, কারণ উইল হ্যাভ মোর হেডস এন্ড টাইম কম লাগবে।
জিনিসটা একদম ওরকম, ঠিক আছে? জিনিসটা হচ্ছে এই অপটিমাইজেশনের সিস্টেমটা ওরকম। আমাদের একটা সোয়ার্ম থাকবে, সোয়ার্ম হচ্ছে একটা কালেকটিভ এফোর্ট। আমরা যখন সোয়ার্মের কথা বলি, সে একটা কালেকশন মিন করে, যে কালেকশন অফ এজেন্ট অর সামথিং লাইক দ্যাট। তো জিনিসটা হচ্ছে এরকম, বাট যখন একজন একটা পাথ খুঁজে পাবে, একজন যখন একটা ইউনো এরর কমানো একজন শুরু করবে, বাকিরা কি সবাই তাকে ফলো করার একটা ট্রেন্ড থাকবে না? বা বাকিরাও ট্রাই করবে না যে তাদের পার্টটা অপটিমাইজ করে? কারণ আমার গোল কি, আমার গোল হচ্ছে এই ফুডটা পাওয়া, রাইট? এবং ফুড হচ্ছে এখানে। তো আমি ট্রাই করব আমার ট্রাজেক্টরিটাকে ওইভাবে রিসেট করে আবার সেখানে আনা। তো এটাই হচ্ছে আমাদের পার্টিকেল সোয়ার্ম অপটিমাইজেশনের থিম, বা এটাই আমরা করব। এটা কি বুঝছো? আমি জানি যে ক্লাসে অনেকেই মনোযোগ হয়তো দেয় না এবং সেটা কনসার্ন না আমার, বাট যে কয়জন বোঝার ট্রাই করতেছো তারা কি জিনিসটা ক্যাচ করতে পারছো? Okay, good. So let's move ahead. So now, if I try to explain from here, I think things will be a bit easier for you. I mean, now you see that things will become a bit more, lucid to you. Okay. So particles from optimization is an optimization algorithm inspired by the collective behavior of animals such as bird flocks or fish schooling. As I have mentioned earlier, that you can see that the bird, they will be flying in a flock in such a way that they follow a certain trajectory. Or if you look at the vortex of a fish, you see that they are kind of following each other, right? Something like that. So in PSO, a population of candidate solutions called particles moves through the search space to find the optimal solution. So this is the thing, the search space. So if I ask you from this question, can you tell me what is the search space? Oh, I erased that. So suppose for our case, R, L, and C, suppose I have a value. I have some lower bound and upper bound. Suppose I have the value of resistor from 1 ohm to 1 kilo ohm. For inductor, it is like, let's say 1 millihenry to, let's say 100 millihenry, something like that. For capacitor, it is like 1 microfarad to 100 microfarad. So can you tell me what is the search space over here, or the solution space over here? So this entire thing is our solution space. I mean, this entire range of boundary that we have, that is our search space. So if I have more agents, in that case, what can be I able to do if more efficiently? I can search this entire search space for more optimized values in less amount of time, right? But that will have some drawback. I mean, there will be always some trade-off. Can you tell me what is the trade-off? সাপোজ তুমি চাচ্ছ যে তোমার বাসায় একটা নতুন কি বলে, লেটস সে নতুন একটা রুম বানাবা, রাইট? তুমি 5 জন ওয়ার্কার নিয়ে আসলা, ঠিক আছে? তারা অবশ্যই একটা টাইমের মধ্যে জিনিসটা করবে। তোমরা যদি 10 জন আনো, হয়তো বা সময় ডেফিনেটলি কম লাগা উচিত, রাইট? বাট ইন দ্যাট কেস কি হবে, তোমার খরচ বেশি হবে না? তো সিমিলারলি যদি আমার সার্চ স্পেস বড় হয় এবং সেখানে যদি আমার এজেন্ট সংখ্যা বাড়ায় বা সোয়ার্ম সংখ্যা বাড়ায়, মানে সোয়ার্মের মধ্যে যে পার্টিকেল, সেই পার্টিকেলের নাম্বার বাড়ে, তখন কি হবে? প্রত্যেকটা পার্টিকেলের জন্য কিন্তু আমার ইটারেশন করতে হবে। তাহলে কি আমার ওই কম্পিউটেশনাল এফিসিয়েন্সি, সেখানে কিন্তু একটা ইস্যু থাকে, বা কম্পিউটেশনাল কস্টটা কিন্তু বাড়ে, রাইট? তো এটা হচ্ছে একটা ট্রেড অফ। যদি আমরা পারফরমেন্স কুইক করতে চাই, ইন দ্যাট কেস আমাদের ওই কম্পিউটেশনাল পাওয়ারের দিকে খেয়াল রাখতে হবে। বাট আমরা এই কোর্সে এমন কিছুই করব না যেটা কিনা আমাদের কম্পিউটেশনাল পাওয়ারের বাইরে যায়। লেটস সে 1-2 ঘন্টা লাগে সিমুলেট হতে, ওরকম কিছু আমরা করব না, বাট আমরা বেসিকটা জানবো। ওকে ওকে each particle adjusts its position based on 2 factors: its own best known position, the one that gave it the best solution so far, and the best known position found by any particle in the swarm. So this is what I was saying from these 2 examples, right? So this bird that we had, it gave us the best trajectory, but this bird was also changing its trajectory as well. I mean, you can see at some point it was going in this way, but whenever it saw that this way is giving the error bigger than the previous one, it is again readjusting the trajectory. So that's the case, that all the particles that we have, they will have the idea of their own best position, and they will also have the idea of the best position for other particles as well. All right, I mean, if I talk about birds or fish, they have the sensors, they may have the they have the eyes, they have the nose, they have the sensors that they need. They can sense or they can figure out the thing. Definitely, yes. Definitely, yes, definitely they can, definitely. And that is why we have the concept of error. All right, so as I have mentioned earlier, you can see that this particle, it was initially going in this way, but since we are taking the position randomly in each iteration, suppose it takes this path, but whenever I am taking this path, it will show that the error magnitude is higher than the previous one. So in that case, what will it do? It can try to readjust the trajectory. Did you get the point? Yes, sir. Even the particle itself, they can also adjust the trajectory, and whenever they are adjusting, they will also have the idea of other particle positions and velocities. All right, so we are going to have some idea regarding velocity for PSO as well in a while, so just bear with me. Okay, the particles fly through the solution space updating their positions iteratively. So you can see that it is written iteratively, right? So after each iteration, they are going to update their position to explore and exploit the search area. So this is a very interesting term, you know, explore and exploit. So let's say that I have 3 birds over here. This bird is going in this way, and this bird is going in this way. So the second bird that we have, it is just exploiting its current position and the current velocity. Is it exploring the search space? No, it is just exploiting its previous velocity, because its previous velocity gave it the best solution. And for this particle, what is it doing? It is just exploring. It is not exploiting. It's just it is just exploring the solution space. But in order to get the optimum trajectory, we have to take the exploration and exploitation both. Because if I keep exploiting this thing, there is a probability that our solution will fall under a pitfall in a local minima. It can never reach the global minimum. So in that case, we have to balance the exploration and exploitation, and it is known as the exploration exploitation trade-off. So this is another important thing that you need to remember. Well, after that, PSU is particularly effective for solving complex, high-dimensional and nonlinear problems, and is widely used in fields like machine learning, engineering design, and optimization. So yeah, in machine learning, we also use that. The gradient descent that we use, that is also one computational method to find the optimization. So gradient descent is used a lot in machine learning. Its main strengths are its simplicity, ease of implementation, and the ability to efficiently search large solution spaces while avoiding local optima or local minima, something like that. So whenever we are into a local minima or maxima, we have some problem. I mean, sometimes we are stuck into that boundary for a while, and it is really hard for us to get outside of that boundary, making it suitable for problems where traditional methods might struggle. Okay, so now let's learn a few things more. Particle swarm optimization works by simulating the social behavior. So this is the thing, right? I mean, we can see that the particles that we have over here, they are following some social trend. I mean, am I wrong? What do you think? They are seeing what other particle is doing. One particle is also following the activity of other particle, something like that. So this is something that we are calling as a social behavior, and they are trying to move through a solution space. A candidate solution in optimization refers to a possible solution or an approximation to the optimal solution. So there is a new term, which is the candidate solution, which can also be said as probable solution. I mean, it doesn't mean that it is the optimized solution, but it can be optimized solution if we find that there is no other value better than this value. And that is why we call it as one candidate solution. Okay. In the context of particle swarm optimization, a candidate solution is represented by the position of a particle in the search space. Each particle's position corresponds to a potential solution to the problem being optimized. So now we have a final thing, and now let us see step by step how we can implement the particle swarm optimization. But before that, do you have any general query from the optimization or particle swarm optimization basic or the concept, something like that? I think no. So in that case, let us move ahead. So the first thing is initialization. So what do we need to initialize? A swarm of particles is initialized with random positions. So can you see that we have some randomness? In the initialization, we have to fix our positions randomly, and the velocity will also be random. So why do we need the velocity? Can you tell me? I mean, what is the significance of velocity? So suppose this is one bird. Exactly, absolutely fine. I mean, that is a very nice answer. So that's the case. Suppose I have a fixed position over here, which I took randomly in the very first case, in the very first iteration. But from this position, if I want to go to this position, what do I need? I need to move this bird from P1 to P2. And how can I do that? I have to induce some motion, right? And that motion is known as the velocity. All right, so using this arrow, I am just trying to show the velocity. Similarly, if you just look at this picture, each arrow is representing one velocity, and after having the velocity, what is the thing that we are getting? We are getting a new position. All right, so this is why the term velocity is also important. Okay, each particle has two key pieces of information: its own current position and the best position it has encountered so far. Okay, so these are the two key pieces of information that we have whenever we are making the initialization. But as we move forward, we are also going to see that there are some other information that is available to our particles as well. All right, so let us move ahead and see what follows. Evaluate fitness. So there is a new term, right? Fitness. So what is this fitness? Fitness means kind of the error. I mean, if I say that the fitness is good, in that case, I have to understand the error is less. If the error is less, in that case, I can say that the solution that I have, it is much more fit to be the optimal solution. All right, so that is why we term the error as the fitness. So if I say that the fitness function, in that case, I have to understand the error from the desired value and the approximate value. All right, from the desired value and the approximate value, we can get the error, and that error is going to give us the fitness. How much fit the solution is to be our optimized value. So that is why we call the thing as fitness. So we have to evaluate the fitness as well. So the fitness of each particle is evaluated by calculating the objective function at its current position. The function measures how good the solution is. Okay. Update personal best. So if I try to iterate in each simulation, what will I get? I will get a new value. I will get a new position. And new position will give me a new fitness, right? A new error, a new value of error or something like that. So if this value of error is minimized than the previous one, in that case, what can I say? I can say that this is now my personal best. This is now personal best. Similarly, if I show you from this example, just look at this. So this is our food over here. So this velocity that we have, it is reducing the error between the the bird and the food, right? So we can exploit this velocity a bit more. It is again reducing the value. But now if I go into this direction, is it going to reduce the value? What do you think? If I take the velocity in this way, is it going to reduce the error? No, because now it is going to fly in this way, but our food is in this way. So that is not going to reduce our error. So in that case, what is the optimum error for this case? That optimum error will be from the second one. Or you can also say from the first one, because I was just following the trajectory of the first position that we had. All right, but this third one that we have, that is never going to be our personal best, because that is not going to reduce our error, something like that. Okay. After that, global best. So this is also important. And why is that? Because this is just one bird, but if we have 10 birds like this, then I also need to know which bird is doing the best, which bird is getting the minimal amount of error, right? So that is also important. So do you agree with me? Was that not the core concept of particle swarm optimization, that we also know what other bird is doing or what other bird is getting as? So that is why we also need the global best as well, because without that we will have no idea what are the value of error that the other particles are getting. So we need to get our personal best, and we also need to get the global best. All right. So yeah, I mean, we are also going to talk more about that. Just have a bit of patience. Let me go through this thing. Velocity and position updates. Each particle adjusts its velocity and position based on the following two factors: cognitive component, social component. So what is the cognitive component? The particle is influenced by its own personal best position. So this is the cognitive component. All right, so you can see that this bird was getting a personal best if it follows this way. So it was taking its personal best cognition. So this is one thing that we know as cognitive component, and another is the social component. And what is that? The particle is also influenced by the global best position found by any particle in the swarm. So if I have another particle, and if that is following a trajectory which is giving less amount of error than the one that we currently have, it will also have that component within itself. It will also know about that component. So that is why we need these two components as well, which is the cognitive component and the social component. All right. And finally, we have this formula, which is the velocity update formula. And this is the velocity update formula that we have. I mean, I am going to explain, but before that, do you have any question from the things that I have discussed so far? Do you have any question? Karo kono question আছে এখান থেকে? Okay, maybe no. So now you can see that the velocity update formula that we have, this is a very linear formula, right? I mean, are we using any analytical method for this formula? What do you think? Just look at this formula. Do you see any analytical terms or any, rigid mathematical terms over here, like the differentiation or integration, something like that? Do I have anything over there? No, sir. Definitely no. That is why this is the computational method. We do not have any rigorous form of mathematics over here. We are just putting one equation that is best fitted for us, and it will depend on problem as well. Okay, so now let's see how we can update the velocity, or how we can update the trajectory, right? We have that, I mean, let me show you this thing. So this is our bird. So now we are going to learn the equation that is going to update this trajectory that we have. So I'm just randomly trying to draw some trajectory, but this trajectory is governed by this equation that we can see over here. So what does this equation say? So you can see that this is VIT plus 1. So this is the next velocity that we need to get. I mean, if we have this point over here, this formula is going to give us the next velocity for the upcoming point. I mean, suppose I am at point 1, I need to go to point 2. So what should be the velocity from point 1 to point 2? That should be given to us by this equation. And we have some terms over here. You can see C1, R1, C2, R2, P based, G based, right? XI, then VI, W. So the first question is, what is VIT? VIT is the current velocity of the particle at time step t. So if I take a different color, suppose this is a different color. So what is the current velocity? So this is our current velocity, right? So this velocity is the VIT. After that, what is this W? This W is the inertia weight, and this says that it controls how much of the particle's previous velocity remains. So this is quite important, because if the value of this W is small, then I am not going to retain much of the velocity from the previous iteration, right? It is saying how much I am exploiting. This is important. This says that how much I am exploiting my previous value. So if this value of W is bigger, then I'm going to exploit a bigger amount of value from the previous velocity, and if this value of W is small, then I'm going to give less significance on that value. So this is what it says. So after that, what is this C1? So C1 is the cognitive component, right? C1 is the cognitive component. This is the personal component. I mean, this is my personal intuition that I am going to take into account. And what is R1? So R1 is the random number between 0 and 1. And why do I need the random number? Can you tell me? Exactly, because the positions that I'm going to follow, that is going to be chosen randomly. But you know, this is not the only term. I know that since we have this random component over here, you will confuse that if I have random component over here, then it is going this way or this way. I mean, we have no fixed way, right? But if you look at the equation, we just do not have the random component only. We have other components as well. So that is why instead of getting any random trajectory like this, we are going to get a tuned trajectory like this. All right, so this is how the thing will look like. Okay, so now let's move ahead. And this is P best I. And what is this P best I? This P best I is the personal best position of particle I. I mean, this is the best solution that I have got so far that is going to reduce the error. All right, for me. So this is the personal best position for me. And what is this XIT? This XIT is the current position of particle I. So at this position, I am comparing how much the difference is between the personal best and the current one. All right. Similarly, if I go to the next component of this equation, what can I see? I can see C2. And what is this C2? C2 is the social component. So previously I was dealing with my personal component, which was this portion, but now I am going to deal with the social component, and that is C2. There is another randomness over here, which is R2, and now I have the global best. So now I know which particle has the least amount of error, and that component is also fused within this equation. All right, can you see? So this is how I am adjusting the whole trajectory that I'm going to have, and that is going to govern in such a way so that I can reduce the error as early and as much as possible. So any question from this equation? I mean, let me clear this thing for you if you have any queries. So do you have any question or anything that you want to ask from this portion? All right, maybe no. Okay, so yeah, so after updating the velocity, we have another thing to update, and that is the position, right? After updating the velocity, we have to update the position as well. So you can see that this was the velocity, this line was the velocity, but this tip of the arrow, that was the position or the current location. This is xi, this is xi plus 1. So I have to update the location as well. And how can I update that? I am updating the location just by adding up the velocity with my current location. So did you get this point? I mean, it is quite easy, right? I mean, if I have this location initially, and if I have a velocity that is going in this way, in that case, what will be my current position? It will be over here, right? So this should be xi plus 1. This is the xi, and this entire thing is what? This is the vi plus 1. So did you get this point? Are you understanding? I mean, are you even there?
Yes.
So I am trying to explain the thing in the class as much as I can. But if you just send me some random email the day before the deadline of the submission for lab report asking me to explain the thing in email, that is kind of rude and that is not going to help you. So it is always good for you if you just can give some attention in the class. All right. So yeah, after that iterative process, this process of evaluating fitness, updating personal and global best, and updating velocities and positions is repeated for a set of number of iteration. So this equation that we have, we are not just going to implement it only for one time. we are going to implement this equation for thousand of time, or the amount of time that we need actually. And this is how we are going to fine tune our value. This is how we are going to reduce the error. All right. So this is our iterative process. And finally, we have to make the termination. So how can I do the termination? It has actually two ways. Finally, if I have 100 iteration, after 100 iteration, the algorithm will stop itself. So this is how it is going to terminate. This is one way. And another way is I am not defining the number of iteration, rather than I am defining the number of tolerance, or the value of tolerance. So if I give a tolerance of 0.1, unless the error that I have is 0.1, it will continue its search. Unless the value is this value, unless the value of error is 0.1, it is going to continue the search, and whenever it is going to get the value, it is going to terminate the search. So this is how we are going to terminate our algorithm. So this is the entire part of particle swarm optimization, and I try to go line by line because I know that many of you will not find the motivation to go through the paragraph. You just try to omit as much thing as possible, but that's not going to help. These things are over there for some particular reason, and I think it is always good for you if you just give it a go. So if you have any final question from the PSO, you can ask. Otherwise, I can start the code for our RLC system, or how we are going to implement the PSO for optimizing our system. Any question from this portion? I mean, from part B? Maybe no. Then let's move ahead. So yeah, we have one series RLC circuit, and our goal should be to minimize the damping factor. All right, so we have to optimize the damping factor of a RLC circuit using PSO. So can you tell me what is the damping factor from your AC circuit basic, or from your circuit basic, which is quite strong, that I believe. Can you tell me what is this damping factor? Any idea on that? So whenever we design a system, that system will induce some oscillation. Due to the input, the system will induce some oscillation, and the damping factor will tell us how fast we can mitigate the oscillation, or how fast we can mitigate the disturbance, something like that. And let me show you from here as well. So if you see this picture, what can you see? You can see that I have just 1 minute. Okay, if you look at this picture, what can you see? So we represent damping using this variable, which is zeta, that looks something like this. So this zeta represents the damping factor, and if we have one under damped, suppose we have some under damped system where the value of where the value of this zeta is less than 1. In that case, what will it indicate? It will indicate that the signal or the disturbance is going to oscillate and then fade away. It is going to die out in this fashion. So this is when the damping factor is less than 1. It is what it means when the zeta value is less than 1. Okay. So whenever this value of zeta is equals 1, what does it mean? It means that how fast we can go to the equilibrium. How fast we can go to the equilibrium. And it is going to take the fastest amount of time to go to the equilibrium that we have. And if I take the zeta equals, if I take the zeta greater than 1, in that case, it is going to rise slowly to the equilibrium. So you can see that over here, the value quickly or sharply raised to the equilibrium. But over here, when the value of this zeta is greater than 1, it is taking some time to reach the value. So can you relate this thing with some physical component? I mean, do you find any physical component that, that where we can implement this concept?
Charging process.
Well, I mean, let's not, confine ourselves within charging and discharging. Right? We have already passed that topic. So there is one thing. How can I give an example? Suppose you have done this lab 221L. Did you do this lab? Did you ever do this lab, the energy conversion lab? Did you do this? Okay, good. So we have some watt meter or some voltmeter or some ammeter, right? And that looks like this. Can you remember? It has one dial and it moves around the values. Can you remember that?
Yes, sir.
Okay, good. So now the thing is, this dial moves, right? This dial moves. And do I want the dial to fluctuate like this? I mean, do I want the dial to move like this, or do I want to be stable in one value pretty quick? আমি কি চাই যে এই ডায়ালটা অনেক নাড়াচাড়া করুক, নাকি কুইকলি একটা পার্টিকুলার ভ্যালুতে আসুক, সেটা ভোল্টেজ হোক, কারেন্ট হোক বা পাওয়ারের হোক, কোনটা চাই আমি?
স্যার একটা পার্টিকুলার ভ্যালু
এবং আমরা কি কোনো অসিলেশন চাই? যখন আমরা ভ্যালুটা দেখি, আমরা কি চাই যে ডায়ালটা কোনো অসিলেশন দেখ বা ভ্যালুটা চেঞ্জ হোক? এটা কি আমরা চাই?
নো স্যার
আমরা চাই না। এক্স্যাক্টলি। সো সেইখানে আমরা এই কনসেপ্টটা ইউজ করতে পারি, যেখানে আমাদের ক্রিটিক্যালি ড্যাম্পড সিস্টেম হিসেবে আমরা যেটাকে ইন্ট্রোডিউস করতে পারি। আমরা এই সিস্টেমটাকে একটা ক্রিটিক্যালি ড্যাম্পড সিস্টেম হিসেবে ডিজাইন করতে পারি, যেখানে আমাদের এই অসিলেশনটা আমরা চাই যত কুইক স্টেবল হয় বা ইকুইলিব্রিয়ামে আসে, সেটা আমার জন্য তত ভালো। আমি কোনো অসিলেশন চাই না। অসিলেশন আসলে আমি কিন্তু কোনো প্রপার রিডিং নিতে পারবো না, রাইট? এটা কিন্তু আমার জন্য পসিবল হবে না। তো এই জায়গায় আমরা চাইলে ক্রিটিক্যালি ড্যাম্পড অসিলেশন ইউজ করতে পারি। আন্ডার ড্যাম্প আমরা কোথায় ইউজ করতে পারি? আচ্ছা, আমাদের যদি কারো গাড়ি থাকে বা ভেহিকেল থাকে, বা যদি কারো বাইক থাকে, আমরা কিন্তু জানি সেখানে একটা সাসপেনশন থাকে, রাইট? একটা সাসপেনশন কয়েল থাকে। তোমরা কি ওটা দেখছো কখন? একটা স্প্রিং থাকে। তো এই স্প্রিং এর কাজটা কি বলতো? আমার যে শক গুলো থাকে, আমরা এটাকে কিন্তু শক অ্যাবজর্বার বলি, রাইট? তো এই শকটাকে সে কি করে? সে এটাকে রিডিউস করে, এবং এটাকে সে কিভাবে রিডিউস করে? এইভাবে করে, সে শকটাকে আস্তে 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 ফেড আউট করে বা কমায় ফেলে। তো এটা হচ্ছে যখন আমার সিস্টেমটা হচ্ছে আন্ডার ড্যাম্পড, আমরা এটা একটা আন্ডার ড্যাম্পড সিস্টেম বলি। এবার তোমরা চিন্তা করে আমাকে বলো যে ওভার ড্যাম্পড সিস্টেম আমরা কোথায় ইউজ করতে পারি বলো তো, যেখানে জিটার ভ্যালু গ্রেটার দ্যান 1। জাস্ট একটা হিন্টস তোমাদের দেই, সেটা হচ্ছে যে ইকুইলিব্রিয়ামে যে ভ্যালু, সে যাবে ধীরে ধীরে, সে ফাস্ট যাবে না। যখন ক্রিটিক্যালি ড্যাম্প থাকে, সে সাথে সাথে বা ফাস্ট ইকুইলিব্রিয়ামে চলে যায়, কারণ আমাদের সিস্টেমে সেটাই দরকার, যেটা আমি অ্যামিটারের এক্সাম্পলটা দিয়ে বললাম। বাট কোন ধরনের সিস্টেমে আমরা চাই যে জিনিসটা ধীরে ধীরে যাক, বা আমাদের সিস্টেমটা ধীরে ধীরে ইকুইলিব্রিয়ামের দিকে মুভ করুক? এটা আমরা কখন চাই? যে কোনো একটা এক্সাম্পল দাও, যে কোনো এক্সাম্পল একটা দিয়ে আমাকে বলো তো।
স্যার অনেক সময়
এক্স্যাক্টলি, ভেরি গুড। আমি বুঝছি, আমি তোমার এইটা বুঝছি। এক্স্যাক্টলি, দ্যাটস দ্য থিং। যদি আমরা চাই যে একটা সিস্টেম ধীরে ধীরে তার ইকুইলিব্রিয়ামে যাক, সেটা আমরা এই ওভার ড্যাম্প সিস্টেম দিয়ে রিপ্রেজেন্ট করতে পারি। যেমন তুমি যেটা বললা দরজার কেস, আর একটা হতে পারে, লেটস সে আমার যদি একটা রোবোটিক ম্যানিপুলেটর থাকে, ধরো আমি একটা রোবোটিক ম্যানিপুলেটর রাখি, বা একটা রোবোটিক আর্ম আঁকি, ঠিক আছে? ধরো এটা একটা রোবোটিক আর্ম। তো আমি চাই এই রোবোটিক আর্মটা এই পয়েন্ট থেকে এই পয়েন্টে আসতে। তো সেটা কি, আমি চাই যে সে একটা ইকুইলিব্রিয়ামটা সে ধীরে ধীরে আসুক, আদারওয়াইজ তার ভিতরের যে ইলেকট্রনিক্স বা মেকানিজম আছে সেটা হার্ম হতে পারে যদি সে কুইকলি মুভ করে, রাইট? তো আমি চাবো সে যেন ধীরে ধীরে যায়, এটা আমার জন্য ভালো, এটা সেফটি ইস্যু থাকে। বা দরজার যে একটা এক্সাম্পল দিলা, সেটাও একদম অ্যাকুরেট, ঠিক আছে? তো এই ধরনের আমার রিয়েল লাইফের সিনারিও দেখে আমরা আমাদের সিস্টেমটাকে আন্ডার ড্যাম্পড, ক্রিটিক্যালি ড্যাম্পড অথবা ওভার ড্যাম্পড এর মধ্যে ফেলতে পারি, ঠিক আছে? তো সেটাই হচ্ছে আমাদের এখানে সেই কনসেপ্ট, যে বিহেভিয়ার বেসড অন ড্যাম্পিং ফ্যাক্টর। ড্যাম্পিং ফ্যাক্টরের উপরে বেস করে আমাদের বিহেভিয়ার গুলোকে কিভাবে চেঞ্জ করব, সেটা এখানে আমরা দেখবো। যেমন আন্ডার ড্যাম্পে কি লেখা? অসিলেটরি বিহেভিয়ার উইথ ডিকেইং অ্যামপ্লিটিউড, সো দ্য অ্যামপ্লিটিউড উইল বি ডিকেইং ইন এ while. Critically damped, fastest return to a steady state without oscillation. So this is what I try to mean, that the dial that we have in our ammeter or voltmeter, that will be in the equilibrium position in the fastest possible time. All right. And in the overdamped, what will we see? We are going to see that there will be no oscillation, but slower return to a steady state. So our system is going to get to the equilibrium or in the steady space, but in the steady space, in the steady state, but that is going to take some time. I mean, that movement is quite a bit slow. So that is what the overdamped system is. So our goal is to optimize the damping factor zeta of an RLC circuit using PSO, and we have the following steps. So we have to optimize the damping factor zeta, and we have to optimize the value of the R, L and C. So আমাদের যেটা করতে হবে, RLC এর যে ভ্যালুগুলো, লেটস সে ওহম, হেনরি অথবা ফ্যারাড, সেই ভ্যালুগুলোকে আমাদের অপটিমাইজ করতে হবে যেন আমি একটা পার্টিকুলার ড্যাম্পিং ফ্যাক্টরকে মিট করতে পারি। সেটা হচ্ছে আমাদের গোল। So now let's see how we can do that. First, the objective is to optimize the damping factor of an RLC circuit by finding the best values for the resistance, inductance and capacitance that result in the desired damping factor. So this value will be given as input by us. The desired damping factor value will be given in input by us. And we need the formula for damping factor because this is going to be the objective function. So can you remember the objective function? So this is the objective function that we have. All right, this formula is going to serve as the objective function, and we are going to optimize the value of R, L and C in such a way so that it meets a particular value of zeta. So that is my goal. And we are going to search inside a search space using the PSO for that optimization. So after that, define the fitness function. We have to define the fitness function as well. So the fitness function will evaluate how close the calculated damping factor is to the desired damping factor. So suppose our desired damping factor is 0.7, and by optimization the values that we got for R, L and C, that is like 0.8. So what should be the error over here? The error is like 0.1, right? So that error will represent the fitness. Okay, and the fitness function is going to evaluate how close the calculated damping factor is to the desired damping factor. So the fitness function is doing nothing, but it is going to just calculate the error. Fitness function টা শুধুমাত্র এররটা ক্যালকুলেট করে আমাকে দেখাবে যে এররটা কেমন। যদি এররটা কমতে থাকে, দ্যাটস ফাইন ফর মি। যদি এরর বাড়তে থাকে তখন আমি কি ট্রাই করব, আমি আমার আর এল সি এর যে ভ্যালু সেগুলোকে আরো ফাইন টিউন করা শুরু করব। ঠিক আছে। The objective is to minimize the error between the calculated damping factor and the desired damping factor. The fitness function takes RLC as input and returns the error value, which PSO will minimize. So this is the thing that I tried to discuss so far. Okay, so now let's see the parameters. So number of particles. So it can also be said as the swarm size. So how many birds do I want to flock? Let's say that I need 20 birds. So we can say that the number of particles is like 20. That can also be 100. That can also be 1000. That will depend based on my problem. Since I need the value of RLC, only 3 variables, I am fine within the boundary of 20 to 100. If I take 1000 or 10,000, that will be overkill. I don't need that. All right. Similarly, number of variables. In this case, we are optimizing RL and C. Bounds for variables, set the lower and upper bound for each variable. So this is the lower bound, right? The 1 is the lower bound and this 1000 is the upper bound. Similarly, 1 micro Henry is the lower bound and 1 Henry is the upper bound. And for C, 1 micro Farad is the lower bound and 1 Farad is the upper bound. So this is how I am tuning the values actually. After that, the inertia weight, which is controls how much the previous velocity will impact the new velocity. Cognitive parameter C1 controls how much the particle is influenced by its own base solution. And social parameter is it controls how much the particle is influenced by the global base solution. After that, we have to initialize the particles. We have to position the particles and we have to take the velocity as well. And Initially, we do that randomly. We place the position of the particle randomly, and in the code, I am going to show you that. All right. After that, we have to run the PSO loop, and that is the main iterative process. So we have to update the velocity using the equation 1. So can you remember the equation 1? This is the equation 1, right? This is the equation 1, and using this equation 1, we are going to update the velocity. And using the equation 2, what are we going to do? We are going to update the position. So I need to update two things, the velocity and the position. All right. And we have to evaluate the fitness as well for the given velocity and position. And we have to update the global best, because at a time, I will not have only one particle searching for the solution. I will have like 20 or 50 or 100 particles searching for the solution in the state space or in the solution space. And I will have the idea of the global best. So I have to update both the personal best and the global best in the very same time. After that, we have to take the output, and once the loop is completed, we have to represent the optimal values of RL and C, and we have to check whether that minimizes the damping factor or not, and sorry, damping factor error or not. All right. And we have to take the output of the RLC, and we have to display the values of the fitness value and everything. And we have to monitor the progress so that if there is any error in our system or not, if we have some error, if it is giving us some unbound error, then we have to, iterate or debug the thing a bit more to make the system a bit more sustainable, something like that. So yeah, any question from here? If not, I'm going to start the code. But I think I tried my best to give you one solid understanding regarding the PSO. So, if you understand so far, I think the remaining code will be pretty easier for you to, understand as well. So any question from here so far? Kindly let me know, yes or no?
No, sir.
Okay, so now let's move ahead. So this is the MATLAB code, and I'm going to show you the MATLAB from the MATLAB online, right? So I have the access to the MATLAB online, and this is quite handy, but I'm not sure whether using the credential of BRAC University, you are going to get the, access or not. I'm not sure. I am using my another credential to run the MATLAB online. All right, but I will say that the MATLAB online has its own limitation. It is not as powerful or as robust as the PC version. All right, but for our case, for the code that we want to see today, it is quite fine. So the MATLAB code that we have, so I try to give abundance of comment so that you understand the code whenever you are going through that. So you can see that lots of comment here and there so that you understand it quite well. Okay. So now let's see. So our goal is to particle swarm optimization for damping factor optimization. So that is our goal to do. Actually, we have to do the particle swarm optimization for damping factor optimization. And first we have to define the desired damping factor. So I am putting 10 over here. 10 is the desired damping factor for me. So if I put 10, what will it indicate? Is it over damped, under damped, or critically damped? What do you think? It is over damped. Yeah. No, it is over damped. Under damped is whenever the value is less than 1. Whenever the value of zeta is less than 1, it is under damped. And whenever the value is greater than 1, it is over damped. All right. So after that, let us put the objective function for PSO, which is the fitness function. So before you get confused, let me clarify a thing. So let me give one star over here. And let me just go bottom in the code and let me try to show you. Let me just see this thing. Okay, good. So now let me explain what I tried to explain, what I wanted to explain actually. So we need some objective function. We know that we need to run the optimization algorithm inside the objective function in order to minimize the error. So that is our goal actually. And we have the we have the damping factor fitness. So this is the name of our function. And you can see that this is an anonymous function since we are writing this with @ and we have the x. And what is this x? This x is the variable. All right. So our function has the variable x, and you can see that we have 3 parameters over here, x1, x2, and x3. So can you tell me why do I have these 3 things instead of 1?
Because instead of 1.
Well, the answer is we have 3 things to optimize, right? We have R, L, and C. So that is why I have these 3 variables. All right, I have R, I have L, and I have C, and that is why I have these 3 variables with me. And now if I try to show you the thing, what can you see over here? What is this zeta? Can you tell me? This zeta is the formula that we use for determining the damping factor. All right, you can see that we have this R, we have this L, we have C. And you can also see that this is R, this is L, and this is C, right? So does it not indicate that x1 is R, x2 is L, and x3 is C? Do you agree with me? This is the function itself, damping factor fitness. This is the name of the function. So the first 3 things over here, which is R, L, C, does they not represent the x1, x2, and x3 from this equation? What do you think?
Yes, sir.
This is R, this is L, and this is C. And after that, this is the desired zeta. So do I have the value of this desired zeta? What do you think? I have the value, right? From the first line that you can see. What is the value? The value is 10. All right. And if I look back into the function, you can see that I am determining the error. Can you see? I am determining the error, and this is important. And what is this error? This error is the absolute value, and we have to take the value of zeta minus the desired zeta. So this zeta will be available to me after calculating with the current value of R, L, and C that is available to me, the global based one. Did you get my point? This is quite important. The zeta that we have over here, it has R, L, and C, and these 3 values will be taken from the global based. All right, and using this value I am going to calculate the zeta using this formula, which is our objective function, and finally we are going to determine the error by doing zeta minus desired zeta. So that will give me what? That is going to give me the error, and I have to minimize the error as much as possible. So that is my goal. So did you get the point?
Yes, sir.
Okay. So now let's move ahead. I mean, so far the thing that I tried to say you, it may sound tricky, but this is quite basic. I mean, once you try to do the code by yourself, or you just go the thing by yourself, I know that you may have some issues. You are always welcome to visit me during my consultation, of course. But things will get a bit easier for you if you just try to understand by yourself as well. All right. So yeah, just let's finish this thing. Let's move ahead. So we discussed so far regarding the objective function. So now let us move ahead to the PSO parameters. So what are the parameters that we have? We have 3 parameters, and that is why the number of variable is 3, which is R, L, and C. Now we have the lower bound. So what is the lower bound for R, L, and C? For our R, the lower bound is 1. For our L, the lower bound is 1 inverse 6, and for the C, the lower bound is 1 inverse 6. So all this value that we have inside this LB, that is going to represent the lower bound, and we also need the upper bound, right? So this is on constrained optimization. We have some constraint, right? And for our upper bound, what can we see? We have the maximum value of resistor is 1000. Then we have the maximum value of inductor as 1, and the maximum value of capacitor is also 1. So this is how we are defining the constraint, the upper bound and the lower bound for our values, and we are going to search within this space to get our optimal solution. Okay, so after that, this is another important thing, the swarm size. So what does it mean? It means the number of particles, the number of bird that I need to have in order to get my solution. And this is the max iteration. So the maximum number of iteration is 50. That means the birds that I have, the particles that I have, the 20 particles that I have, that is going to iterate 50 times each to get the optimal value, to reduce the value. So that is what it is going to do. Okay. And after that, what is the inertia weight? That is 0.5. What is the cognitive parameter? That is 1.5. And what is the social parameter? That is 1.5. And these values, I have tried to take some reasonable values. You can also play with these values as well to see how it impacts on the value. Okay, so after that, initialize particles. So what can you see? Random positions and velocities. So I tried to make this thing over here so that you understand that in the very first case, whenever we are trying to initialize the random position and velocities, we can take the things for all the particles randomly. Okay, just let me explain the thing. So what does this thing mean? Whenever I am taking rand swarm size inverse, what is it going to give me? What is the swarm size? 20. And what is the inverse? 3. So this is going to give me a matrix that has 20 row and 3 column, right? Do you agree with me?
Yes.
So for particle 1, I am going to have a random value of resistor. Let's say that is 2. For particle 1, I am going to have a random value of inductor. Let's say that is 0.0003, something like that. For particle 1, I am going to have some random value of capacitor, that is like 0.00004, something like that. That is the value for particle 1. So how many particles will I have? I will have 20 particles, and all the 20 particles that I have, that is going to take random values initially. That is going to take some random values, and that random matrix is multiplied with what? The upper bound minus the lower bound. So that is the range. I am going to do some element wise multiplication with that thing, and I am going to add it with the lower bound. It is something like that. Let's say our lower bound is 1. What does it mean? It means the value that I have, the value can never go beyond 1, right? I mean, the value can never go beneath 1 actually. It can never be less than 1. So that is why I have the lower bound, because the value that I have for position, it will be always higher than 1, right? And after that, why am I doing the UB minus LB? Because that is the range, right? The value that I have over here, that will be within the range of those values. So that is why we have this line over here for position, right? So after that, you have to remember one thing. We are in the initialization phase. Whenever I am doing the initialization, this is the very first condition, and it is going to change. The initialization condition will change after every iteration. You have to always remember that. All right. So we are still in the initialization phase. So first we initialize the position. After that, we are going to initialize what? We are going to initialize the velocity, and we are also going to write one zero matrix. And why is that? Can you tell me? In the initialization, why do I have a zero matrix? Because initially all I have is some bird, right? All I have is some particle sitting. All I have is some particle sitting randomly in my space, in the solution space. Do they have any velocity with them? In the very initial condition, can you see any velocity? The answer is no. In the very initial condition, there is no velocity. After the first iteration, it is going to move to a new point with some velocity, and until that we have to keep the velocity 0, and for that reason we have this thing over here. We have this 0 over here. Okay, so after that we have the p-best and we have the g-best. And what is this p-best? P-best is the positions. So in the very first case, I mean, if I ask you one thing, suppose you start from position 1. So at this point, what is your best position? If I ask you this question, what is your answer? Suppose I have only one pen in my hand. In that case, what is the best solution that I have? Can you tell me? The thing is, whatever I have currently, that is the best thing that I have. I mean, I do not have any way to compare the thing. So that is why the thing that I have currently, even though it is just one, that is my personal best at this very moment. If I have just one pen in my hand, that is the personal best that I have now. But if I have 5 pens, from that 5 pen I can compare. But if I have just one pen in my hand, there is no way to compare, right? And that is why the personal best for the first condition, we have the only positions. All right. Similarly, what is the global best? Global best is just one value, and that is taken from all the values, right? Do you understand? Suppose I have 20 personal best in this case, but from this 20 personal best, I will have one that is the best of those 20 samples. This is the case. So did you understand this point? I mean, do you have any question from here? You can try to respond, otherwise I will not know whether you have any issues or not.
Sorry, can you repeat the global best part?
Yeah, sure. Just before that, I want to ask you one thing. Suppose this is A, this is B, this is C, this is D. So A has like 10 taka, 20 taka and 50 taka note. All right. Suppose B has 20 taka, 50 taka, 100 taka note. C has 500, 10 and 50 taka note, and let's say D has 50 taka, 10 taka and 1000 taka note. Good. So now if I ask you what is the best, what is the personal best for A, what should be your answer? What is the personal best for A? So what should be your answer?
50.
Very good. That should be 50. What is the personal best for B? That is 100. What is the personal best for C? That should be 500, and for D it should be 1000. So in this line, the P best that you see, that is the personal best, and that is for all the particles that I have. So can you see this position in any other lines in this code? This position, can you see this anywhere? Yes, this is in the very first line, right? In the very first line I have the position. So whenever in the very first scenario I am just randomly orienting the particles, I have no way to compare. So that is the best thing that I have. So that is the thing that I wanted to mention. Suppose in the very first position you have like 10 taka, particle B that has like 20 taka, particle C has like 50, particle D has like 500. So in the very first case, what is your best? Is your best not the only thing that you have? So that is my question. Did you get the point?
Yes, sir. I was actually confused about the global best part. Like, why did we take the first row?
Yeah. So now the thing is, we have the personal best, but now we know that in our particle swarm optimization, we know the social behavior, right? I also know how much money other people has or have. All right. So if I ask what is the global best from this particle sample, what should be the answer? That should be 500, right? That should be 500. So did you get the point? This is what the thing is over here. So in the G-best, we are going to take the global best. We are taking the global best for all the scenarios. So that is the thing. Similarly, if I try to give the example from this scenario, what should be the global best? Let's say I did like 3 iterations. All right, this was the first iteration that I took randomly, but after that I tried to fix the things. And I got 1000 over here. So is this 1000 not my global best in this case?
Yes, sir.
Okay, good. So since this is the 1000 and this is the biggest value that I have, using the concept of PSO, what will the other particles try to do? The other particles will try to follow the same path that gave this D1000, right? Did you get the point?
Yes, sir.
Okay, so that is the thing that we want to do. But for that, we have to store our global best in some point, right? So we are dealing with matrix. So we have to store our global best in some point. So that is why we have another, how I say it, we have another matrix and we are going to take the global best. So now there is one thing. I mean, I believe that you have done some programming course. So if I ask you this thing, how can we determine which is the bigger value, 5 or 2? How can we do that? I mean, if I write a program in C, did you ever see that we write some if condition? I mean,
Yes, sir.
so we just write it in this way. If 2 less than 5, the thing is like true. If 2 greater than 5, the thing is not true, which is like false, something like this. I'm just trying to make one analogy. So first we have to take some value and we have to set that value as the best, right? So that is what we are doing. I mean, over here you have seen that I am comparing the value of 10, 20, 500 and 50, right? But for our case, let's say that the first value is the best value, which is 10. After that, I am comparing with 20. So among 10 and 20, which is the bigger value? Definitely 20, right? After that, we are comparing the value with 500. So which is the bigger value now? 500. Again, I am comparing 500 with 50. So which is the bigger value? 500. So what did I do? In the very first case, I took the first value as the best value, right? Did you see the point?
Yes, sir. It's clear now.
Exactly. So that is why I am writing 1 over here, because as I have mentioned earlier, I am still in the initialization phase, right? I am not into the iterative phase now. I am not inside the loop. I am in the initialization phase. So I have initialized the positions randomly. That was the first thing. And there was only some point. We do not have any velocity now. So all the velocity is 0. As you can see that we have a 0 matrix. After that we have a p-best, which is the individual best values of R, L and C. And for the global best, this is the trick. What did I do? I assumed that the first particle value that we have, that is the best value. So that is why I have this 1 over here. All right. And that means I am assuming that this 10 is my best value. But as I run into the loop, whenever I am running inside the loop, this value will be overridden by the bigger values or the better values. So that is why I tried to make this analogy. I hope this thing is clear to you. Any more question from here? maybe.
No,
Now
sir.
let's move. Now let's move ahead and let's see. So now we have the P-based score and the G-based score and the best IDX. So, well, so how can I get the personal best score? Just let me erase this thing. Let me erase this thing. Okay. So the P-based score is we have a array function and we have I. What is this I? I is the, just let me show you. So I is the number of the iteration actually. All right. Whenever we are starting the for loop, we need one variable to iterate over. So that is the I. All right. And for our case, the value of I will be from 1 to 50, right? I mean, from our code, the value will be from 1 to 50. So that is the I over here. All right. This is the I. And after that, we have the objective function, and you already have seen the objective function, which is the damping function equation itself. We have the position. So this is all the positions that we have, and this is the number of times that we are going to run the iteration. So, you know, this is just single line, but this line has so many values. I mean, all the iterations that we get from the loop will be stored inside this P-based score. So that is the, you know, objective of this point. All right. So if I am in position 1 for RLC, let's say I have particle 1 that will have one RLC, and for first iteration that is going to have one value, but for the second iteration particle 1 will have a new value of RLC, which is like R2, L2, C2, right? So for 50 times for particle 1 we will have 50 different values of R, L and C. But do I have only particle 1? The answer is no. I have 20 particles. So for 20 different particles, I will have 50 different values for R, L, and C each. And those values will be stored in the P-based score. All right. So did you understand the thing? Did you understand the point? I hope you do. So after that, I have the personal best, and I also need the global best, right? Because in my function or in my equation for PSO, I have this term G best, right? So I also need the global best as well. So how can I get that? I just need to take the minimum value from the personal best score. So now there is this question. You will ask me, why am I taking the minimized value instead of maximum value? So can you give me the answer? The answer is, I am trying to minimize the error, right? The less the error, the better for me. So that is why I am going to take the minimum value where the error is reduced. Where the error is reduced, I am going to get the minimum value, and from the P-based score, from this entire big set, I am just going to take the value where I get the least amount of error. And this is the best index. This IDX means index, and this best index means for which iteration and which particle. I have 20 particle, right? P1 to P20, something like that. And I am doing 1 to 50 iterations. So for which iteration, which particle is going to give me the best value, that is going to be stored into the data. So that is going to give me the best index. Let's say particle 15 is going to give me the best value. All right, the minimum amount of error I am going to get from particle 15. So that is why maybe I can take the best index from that particle. So that is also what we are going to store in our matrix. So we have initialized the particles, we have made the fitness, we have analyzed the fitness as well. So now it's time for us to dive into the loop. All right, so now the things will be a bit easier for you because we have discussed the core basics that we need for the code so far. So the remaining things will be a bit easier for everyone, I hope. So this is the PSO loop, and this is the iteration. We have the max iteration. So what is the value of the max iteration? So if I look, it is 50, right? So the maximum number of times that I am going to run the loop is 50 times. Okay. And there is another for loop. So this is one nested for loop, right? So this thing is going to run for 50 times. What about this thing? How many times will this value run? The swarm size 20.
20.
That is going to run. That is going to run for 20 times, right? So I am going to have like 1000 instance, right? 50 into 20. So that's the thing that I'm going to have, and this 1000 values will be personal based value or personal based score, and that will be stored using this function. I mean, I am going to calculate the error using this function, and those 1000 personal based value of R, L, and C will give me 1000 values of error, and from those errors I am going to take the least or minimum amount of error, and that is going to give me the best score for the entire R, L, and C thing. All right. So now let's move ahead and let's see something more. So now this is the equation of PSO that we are going to implement. We need the velocity, right? I mean, if I want to move from this point to this point, I need some motion, right? I need some movement, and that movement is the velocity. And I need to determine the velocity based on what? On W, C1, C2, G based, P based. So we had a very rigorous discussion on how the algorithm works, or how this mathematical terms are into account or something like that. So this is nothing but the implementation of equation 1 that we saw from part B. All right. So this is the implementation of this equation. Okay. This is the implementation of that equation, and as you can see that we have the velocity of I. And so you can ask me, what is this colon, right? I mean, I can understand that this I is the number of swarm, the number of particle whatsoever, but what is this colon? Can you tell me? This colon will represent R, L, and C, and that is why we have this colon. I mean, it is going to represent the three variables that I need using this colon. All right. So after that, we have the velocities, we have the C1, we have the P waste, and initially I just want to ask you one single question. Whenever the loop is running for the very first time, what should be the value of this I? That should be 1, right? I mean, I am running for particle 1. But will this value not be directly taken from the initialization? What do you think? For the very first iteration, I am going to take the value from the initialization, and I'm just going to put the values over there. That is how I'm going to do. All right. And later on, as I run or as I iterate the thing more and more, as I have shown you using the pictures, all the particles will try to converge into one particular solution. You have to remember one thing. Whenever we are using the particle swarm optimization algorithm, the swarm will converge into one point. I mean, it is something like that. Like if I have 5 points, all those 5 points will move into one single point. I mean, they will try to converge. Unless they converge, we cannot say that we are going directly to the solution. All right. So yeah, after that, after running this PSO algorithm, what is the next thing that I need to do? This was the equation 1. After that, we have to update the position as well using the equation 2, right? So this is the equation 2, which is, as you can see. And this equation 2 is also taken from part B as well. This is the equation 2. This is the equation 2. Okay, there, let's move ahead. Okay, ensure particles stay within bounds. So now there is a problem. So this is one mathematical process, and there can be some issues whenever the solution gets out of bound. So what was the boundary for resistor? Can you remember that? It was 1 to 1000, right? But what if the new position that I have is like 1005? In that case, what is the problem? The problem is now I am not respecting the boundary. I am getting outside of the boundary. I do not want that. So how can I fix the problem? So whenever I am leaping outside of the boundary, I am going to take the maximum value as the current value. Did you get the point?
Yes, sir.
I mean, I will explain the code, but first let me ask you, did you get the point that I wanted to share? Suppose
Yes, sir.
you have 1000 and 100 as your current position for particle 1. After adding up the velocity, you got this position, but this is outside of your boundary, right? In that case, what are you going to do? You are going to truncate the value and you are going to take the maximum value as 1000. You are taking the maximum value. All right. So I have another question for you. Among these two values, 1100 and 1000, which is the minimum value? 1000, 100 এবং 1000 এর মধ্যে ছোট ভ্যালু কোনটা? 1000 is the minimum value, right, between these two values. So that is why we have this thing over here. Can you see that we have a minimum function? Let me take another color. Can you see that we have this minimum in the upper bound? Can you see this thing? So that this is something that sometimes people also confuse, that whenever I am taking the upper bound, why am I taking the minimum value? Because the minimum value for upper bound is the 1000 over here. If I have something getting outside of the boundary, that value is getting bigger than the upper bound that we have. So I have to take the minimum of those boundary, and that should give me 1000, right? This is the case. And similarly, let me ask you one more question. Suppose the least value was 1, but let's say you are getting 0.5. In that case, what is the problem? Can you tell me? In that case, the problem is the value of resistor is less than the lower bound, right? So in that case, what should I do? Can you tell me, using your intuition, what should I do?
Maximum.
Exactly, very good. In that case, I am going to take the maximum value 1, right? So between these two values, 0.5 and 1, what is the bigger value? Definitely 1. And that is why whenever we are working with the lower bound, we are going to take the maximum thing. So this is how I am writing the code. First I am checking whether the first I am checking whether the value that I have, whether that is inside the upper bound or not. All right, if that is beyond the upper bound, that it is going to take the minimum value, and that is going to be the position for the current I. All right, but if that value is less than the minimum value, then I am going to take the maximum value, which is going to be the value of lower bound. In our case, that value is 1. So this is how I am going to ensure that the particle that I have, that is going to stay within the bound. So this is the way that I follow. Okay. So any questions so far? I mean, I think we are halfway through the code. So any questions so far? Okay, maybe no. So let's move ahead. So now we have one final thing, and that is the fitness function. So I am going to take the measure of fitness, and in our case, what is the fitness? In our case, the fitness is nothing but the error actually. All right, the error that you see, that is actually the fitness. All right. So yeah, now let's move ahead. So now we are just going to run one if condition. I mean, the same if condition that I tried to show you when giving you the example of your C programming basic, like how you can differentiate which value is higher. And that is the exact thing that we are going to do. So now we are going to check. Well, before that, I have another question. And what was this thing? Can you remember? What was the personal best score? This personal best score was the error, right? As I have mentioned earlier. So I am checking whether the error that I have, whether that is bigger than the fitness or not. All right. So if I see that the current error that I have, that is bigger than the fitness, in that case, what should I do? I am going to update as the error with the fitness. Similar like this. Suppose I have three numbers, 1, 2, 3. I am checking if, suppose I need to determine which is the biggest value among these three, right? First, what am I doing? I'm going to check whether the value 1 is less than 2 or not, right? So if this is, I need one variable as well, right? So suppose in the case, this I is 1, so I am checking if the I is less than 2 or not. So if this is less than 2, what am I doing? I am updating the 2 with this I. Can you remember that you did this thing in your C programming class? Can you remember this thing? That we have one variable and we are updating the variable with the new value, and that is exactly what we did. We need the smaller amount of error, and if we find that the fitness that we have that is less than the current error, I am going to replace the current error with the fitness. So that is exactly what I'm doing. All right. And after that, the personal best that I have, that is going to be updated with the position as well. Each position will have the own error value, and the personal based value will be updated with that error value as well. Just refer to the thing that I have mentioned whenever I was initializing the values over here. All right. And finally, we need the global best thing. And how can we determine that? So we have the current best score, we have the best index, and we have the minimum value of best score. So, if I ask you how many instances will be there in the p-best score, there will be 1000 instances, right? And among those 1000 instances, I have to take the minimum instance, and that is going to give me the minimum error, and that error is going to be the best value for me. Okay. And for that thing, I am also going to get one best index for that particle as well. Okay. But as I have mentioned earlier, the thing will be continuously iterating. And after each iteration, if I get a new best value, that is going to override the current best value, and that is going to replace the thing similarly that we did over here. Okay. So the personal best and the global best, they will iterate after each loop. Okay, so I want to show you another thing. Let me show you the code. So the code, you can see the for loop is starting from here, right? And the for loop is ending over here. Did you notice this thing from the code? The indentation is not visible from the PDF, right? I understand that, but from the code, can you see this thing? The for loop is starting from here. Oh, sorry. The for loop is starting from here and the for loop is ending over here. So the update that we have, the if condition that we have for the global best and personal best, are they not updating after each iteration? What do you think?
Sir,
বলো কেউ কিছু বলবা? Okay, maybe no. So you can see that the for loop that I have, that is holding the condition, the if condition for personal best and global best. So after each iteration, it is continuously checking whether the global best is, surpassing the personal best or not, or the global best that I have, is it surpassing the current best score or not? And if that is surpassing, that is also going to update the best index as well accordingly for that particular particle. Okay, so this is how I am going to make all the values iterate all over the time using the PSO, and that is going to optimize the values. And after that, if I show you from the code from here, after that I'm just going to display this thing in the output in the command window that you are going to see. So these things are nothing, they are the global based values for R, L, and C, but for each iteration. So this is very important. So what is the thing that I am showing? After each iteration, I am showing the best values for all the 20 particles for R, L, and C. All right. And I am also showing the final fitness, which is the error. All right. And finally, this was the function for error, or this was the function for our objective function that you can see. We are determining the zeta, we are representing the value of R, L, and C. Just we are determining the error. That was our theme. So let me run this code for you, and then maybe we can do some more explanation. It's fine. Let me run it for you. So yeah. So now my first question is, you can see that the thing has been run for so many times, right? You can see, can you see my screen? So after the first iteration, what did you get? After the first iteration, you got the global best value for resistor as 810, the global best value for inductor as 0.256, and the global best value for capacitor as 0.859, right? So those are the global best values among the 20 particles after the first iteration. And how many iterations do I have from the code? From the code, I have maybe 50 iterations, right? So after 50 iterations, can you see that the value is changing? First it was like 810, after that it was 638, after that again the value was like 898. Like initially the value was fluctuating a lot. Can you see that? And why is that? Because of the exploration and exploitation balance. First I was both trying to explore and exploit, and as I get near the horizon, or get near the optimal value, what can I get? Can you see? The value of resistor is 1. Well, just give me 1 second. I think, yeah, let me run the thing. Yeah, that is what actually happened. Just give me one more check. Yeah. So now you can see that after a good amount of iteration, the value has been converged within these values. Can you see that? The resistor value is 1, the inductor value is 0.0277, the capacitor value is 1, and this has been going on for a while, right? And you can see the calculated value of zeta. So the error is also reduced. Can you see? So after 50 iteration, you can see that the error value is like 1.510 inverse 7. So I can say that the optimized value for R, L, and C is, acceptable for us. But if I compare in the very beginning, what was the value? The value was pretty huge, right? Can you see? The value was pretty huge, like 650, 0.88. And similarly, what was the calculated value of zeta? Can you just check? What was the value? That value was 653, but what was our desired value? The desired value was 3, right? You can see over here. So these two things, do they match? What do you think?
No, sir.
53 and 3, they do not match. The error is huge. But after like 50 iterations, I can see that I have reduced the error to a very small amount, and I am quite fixed with the optimal values of R, L, and C. This is how I did this thing. No analytical calculation, only trial and error after like 50 iterations. So this is for the over-damped situation, right? So let's do for one under-damped case. Let me give the value as 0.1 as desired zeta. And let us see what happens next. Let's see. Okay. So now if I run this thing, you can see that the value of RLC is like 111. But this is not from the very beginning. In the very beginning, they had some different value, and with the time and the iteration, the value was kind of converged into one optimal solution. Similarly, let us try for one critically damped case when the zeta value is 1, right? So if I run this thing, you can see for the critically damped case, the optimal value of R, L, and C is like 1, 0.27, and 0.89, something like that. Okay. So this is how we can implement the thing, and I tried to explain the code line by line, and yeah, okay. But I do not think that I need to explain you these 3 lines, because these are the display function, right? I mean, they have nothing significant. All right. I mean, they are just some really elementary topic. How you display something in MATLAB. I think you already know that because you had like some previous courses or even you had like one basic course on MATLAB in the very first class that I recall. So I think these things should be fine. All right. But this is the core code that I wanted to show you, and this is how it changes. So there is one thing that I want to say. After each iteration, the initial value may be different because we are taking some value randomly, right? The randomness is there, and that is why the initial value can be a bit different. So just take this value into your mind, like 405, right? This was for this simulation. So let us close this value, clear all value, and sorry, and let's do the CLC thing. Okay, now everything should be cleared. So now if I run this code one more time, and if I check the value is 230, right? Previously the value was like 450 something like that. I do not recall exactly. But now the value is 230. And why is that? Because in the very first case, we were determining the position randomly. But as time went on, we were trying to converge into a particular solution, and this is how we did the conversion. Okay. So this is the basic of the PSO algorithm, and you have one lab report where you have to optimize the time constant of an RC and RL circuit. You know the formula for time constant, right? And you have to take one RC circuit and you have to take one RL circuit. You have to write down the equation for RC and RL circuit for the time constant tau. And after that, you have to remember that the time constant for both RC and RL circuit should be 1. Okay, so you can have your freedom to choose the range of RLC with the other parameters like C1, C2. All right, the W, you have the full freedom to choose those values. Just try to play with the values. Okay, so that should be the lab report that you have to submit next week. And this should be the whole discussion for the PSO. I think we had a big lab, right? Like more than 2 hours, 30 minutes. But let me know if you have any queries, any confusion or any question from any part of this experiment. Do you have anything to ask? Did you understand the topic? I mean, what do you think? I mean, what is your opinion regarding this topic? Okay, you don't have any opinion. That's
The code was understandable.
okay, good. But try to go by yourself one more time. Try to run the code. All right. Try to run the code by yourself, and I think you will find it interesting. And if you have any issues, you can visit me during my consultation time. And I will really appreciate if you send me one email before visiting the consultation time, because sometimes I see people not arriving in my consultation time and later on blaming me that I'm not there in my consultation. So that is quite rude as well. So, you have to just send me one email just to keep the track, because I don't want to take blame for something that I am not, if I didn't do that, I am not ready to take the blame. So yeah, if you visit me in the consultation, send me one email just to be assured that you will be there, because I am always there in my consultation, but I see no one arriving to me. But later on, people saying that I'm not there in the consultation. So yeah, please try to keep that thing in your mind.
Sir,
Any more questions?
স্যার ল্যাব রিপোর্টে যে টাইম কনস্ট্যান্টের কথা বলা সেটা হচ্ছে এই কোডের এক্সিটার মতো না, লাইক টাইম কনস্ট্যান্ট 1 যেটা দেওয়া
টাইম কনস্ট্যান্ট যেটা 1 সেটা হচ্ছে ডিজায়ার্ড জিটার যে ভ্যালু সেটার মতো। আমাদের এখানে ডিজায়ার্ড জিটার ভ্যালু কত ছিল বলো তো?
স্যার
3 ছিল, কখনো 10 ছিল, কখনো 0.1 ছিল, রাইট? অনেকগুলো ভ্যালু ছিল। সিমিলারলি তোমার টাইম কনস্ট্যান্টের যে ভ্যালু থাকবে আরসি এবং আরএল সার্কিটের, সেই ভ্যালুটা কত হবে? সেই ভ্যালুটা 1 হবে। আরসির জন্য 1 হবে, আরএল এর জন্য 1 হবে। তোমার অবজেক্টিভ ফাংশনটা ডিফারেন্ট হবে, কি হবে সেটা আমি বলবো না, সেটা খুবই ইজি, বাট সেটা তোমার ফিগার আউট করতে হবে, করে সেইভাবে জিনিসটাকে অপটিমাইজ করে আমাকে সলিউশন দেখাতে হবে যে আরএল আর সি এর ভ্যালু কত। ঠিক আছে? মানে বুঝছো জিনিসটা?
ইয়েস স্যার।
ওকে, গুড। সো এনি মোর কোয়েশ্চেন? Well, I think there is no question. Then thank you very much for your attendance. And yeah, কেউ কিছু বলবা?
স্যার প্রজেক্টের বিষয়টা নিয়ে একটু মানে প্রবলেম হচ্ছে।
আমি বুঝি নাই কি হয়েছে, কি কিসে প্রবলেম তোমার?
প্রজেক্টটা নিয়ে মানে
হ্যাঁ, তুমি কি ওদিন আসছিল ভাইয়া, মানে যেদিন মানে প্রজেক্ট নিয়ে আলাপ করি ছিলা তুমি, মানে মানে কই বুঝতে পারো না আমাকে বলো তো।
মানে স্যার আমি বলছিলাম কালকে কি আপনি থাকবেন?
কালকে আমি থাকবো, তুমি কনসালটেশন টাইমে আসো, তাহলে তুমি প্রবলেম নিয়ে আসো। বাট আমার কাছে আসার আগে বেসিক যে জিনিস, তুমি যদি এসে আমাকে এমন কিছু জিজ্ঞেস করো যেগুলো আমি ক্লাসে সময় নিয়ে বলছি, আমি হয়তো এন্টারটেইন নাও করতে পারি। আগে তোমার গ্রুপ মেম্বারদের সাথে আলাপ করো, বাকিদের সাথে দেখো সেটা আমি আলাপ করছি কিনা, তারপরে আসো। ভালোভাবে নিজে একটু অ্যানালাইসিস করে তারপরে আসো। এসে যদি আমাকে ফার্স্টে বলো যে স্যার পুরোটা আরেকবার বলেন, সেটা খুবই রুড দেখায় এবং সেটা আমি হয়তো করব না। পুরো আধা ঘন্টা প্রজেক্টে যা বলছে সেটা আমি তোমাকে একাই আমি হয়তো বলবো না। সরি টু সে, বাট দিস ইজ হোয়াট ইট ইজ। ক্লাসের সময় নিয়ে এই কারণেই দেখাই যেন সবাই একটু শোনো, ঠিক আছে? যদি ক্লাস ওটা রেসপেক্ট করতে না পারো, দ্যার ইজ নাথিং টু ডু। ঠিক আছে, ওকে, গুড। এনিওয়ান এলস? আর কারো কোনো কোশ্চেন?
স্যার আমি একটু অ্যাটেন্ডেন্স নিয়ে ছিল।
আচ্ছা, অ্যাটেন্ডেন্স আমি আর দিচ্ছি না, মানে আজকে যদি কেউ মিস করো, দ্যাট শুড বি ইট। আর কোনো কোশ্চেন কারো?
স্যার আমি হয়তো স্যার ওই সময় স্যার অডিও বলছিলাম না স্যার।
আচ্ছা, ইটস ফাইন। সো থ্যাংক ইউ এভরিওয়ান। নেক্সট উইক তোমাদের পরীক্ষা, সবাই ভালোভাবে প্রিপারেশন নাও। যে সিলেবাস, আমি কোয়েশ্চেন প্যাটার্ন নিয়ে হয়তো বা আজকে একটা পোস্ট দিয়ে দিব, আর ক্লাসে যেরকম আমি আলাপ করলাম পরীক্ষার প্যাটার্ন নিয়ে সেরকমই হবে। বাট আমি পোস্ট এটা দিয়ে দেবো যেন তোমরা দেখতে পারো, এন্ড দ্যাটস ইট। ঠিক আছে, নো ওয়ারিস। যে সময় দেওয়া থাকবে কোয়েশ্চেন ওই সময় সলভ করতে পারবা, যদি প্রিপারেশন নিয়ে আসো। আর যদি প্রিপারেশন না আসো, সেটা কিছু করার নাই। এবং একটা ইস্যু হচ্ছে, পরীক্ষা যদি প্লাজিয়ারিজম করো বা চিটিং করো, এটার কনসিকুয়েন্স সিভিয়ার। সরাসরি আমি 0 দিয়ে দিব, এন্ড দ্যাটস ইট। যদি পরীক্ষায় সিন ক্রিয়েট করো, 0ই থাকবে ওটা। তো ওইভাবে প্রিপারেশন নাও যেন পরীক্ষা ভালোভাবে দিতে পারো। আমি চাই যেন তোমরা সবাই ভালো করো, দ্যাটস ইট। এবং তোমাদের প্রজেক্টের আলাদা করে সময় দেওয়ার উদ্দেশ্যই একটা, যেটা আগে বললাম, যে আমি চাচ্ছি যে প্রজেক্ট প্রেজেন্টেশনের দিন যেন সবাই একটা ফেস্টিভ এনভায়রনমেন্টে আমরা থাকি, রাইট? আমি চাচ্ছি ডিপার্টমেন্টের আমার অন্যান্য কলিগদেরও ইনভাইট করতে, দ্যাটস ইট। তো আমি চাই একটু ভালো প্রজেক্ট যেন সবাই শো করি। এমন না যে খুব, যেটা আগে বললাম, যে এটা কোনো রিসার্চ প্রপোজাল না, রাইট? মানে খুব সফিস্টিকেটেড কিছু চাচ্ছি না, বাট আমাদের কোর্সের রিকোয়ারমেন্ট যেগুলো, সেগুলো যদি মিট করে, দ্যাট শুড বি নাও। বাট অনেক সময় দেখা যায় যে অনেকে সরাসরি কোনো ইন্টারনেটের ব্লগ থেকে বা অন্য জায়গা থেকে সরাসরি প্রজেক্ট নিয়ে আসে। তো সেই জন্য একটা স্ক্রুটিনি করা যে তোমাদের প্রজেক্টটা কেমন হচ্ছে, দ্যাটস ইট। ঠিক আছে, এটাই। যাই হোক, ঠিক আছে, সবাই ভালো থাকো। সবার সাথে হোপফুলি সুন দেখা হবে। ওকে, গুড বাই।
আচ্ছা।